Hello and welcome to International Geoscience Colloquium organized by Christ College Autonomous, University of Kerala, University of Exeter, UK, University of Zululand, South Africa, supported by Ministry of Earth Science, Government of India. So today we have some interesting sessions ahead. Before we begin, let me give you some instructions. All the participants are requested to mute your microphone as well as off your video so that we do not get any disturbance in between. And a feedback link will be provided towards the end of the session so you can fill it. You can also post your questions in the chat box in Zoom as well as in YouTube, and we will come to those questions at the end of presentation. So without further delay, let's start a program. With all due respect, let me invite our session chair, Dr. Sajin Kumar KS, Assistant Professor, University of Kerala, Adjunct Assistant Professor, Michigan Technological University, USA. Over to you, sir.
Thank you very much, Asha Merenjali, for the introduction. And again, I am welcoming you all to the two-day seminar on Geohazards, Mitigation, Management of the International Geosciences Colloquium organized by Christ College Iringalakkoda, University of Kerala, University of Exeter, UK, University of Zululand, South Africa. And also I express my sincere gratitude for giving me an opportunity to handle a session. So today we have 4 talks by eminent personalities in the field. So without much delay, I hope we will be better enter into the session. So the first talk will be the keynote address for today's session, and it will be done by Dr. Shekhar Lucas Kuriakos. I will give a brief introduction about Dr. Shekhar. He graduated in BSc Geography in 1999 from University College Trivandrum, and then postgraduate from MSc in Geography from University of Madras, India. He obtained another MSc in Geoinformation Science and Earth Observation with a specialization in hazard and risk analysis from University of Twente. Later, he obtained PhD from the same university, that is University of Twente, and the topic of his research was physically based dynamic modeling of shallow landslide initiation in the Western Ghats, Kerala, India. He is recipient of several fellowship and award, and I am mentioning only a few. International Tropical Timber Organization Fellowship, ITC IARS Joint Education Program Scholarship, International Visitor Leadership Program, full grant from Department of States, United States of America. And he has several publications to his credit. And the most noteworthy was the one which have the highest citation for the landslide studies in Kerala. And from the screen, I was looking, I'm searching for Shekhar Lucas Kuriakos. Shekhar, you are here? Hello. Actually, he may be joining from the department login. Please, 1 minute, please hold on. Because he is presently the member secretary for the Kerala State Disaster Management Authority, and he has several programs in between. So today afternoon also I have bringed up. So I am muting my mic for a second.
Sajin sir, can I give some instructions to the candidates meanwhile? Okay, so those who have attended yesterday's session, please fill the feedback as soon as possible. And today's link will be given towards the end of the session. So please do not forget to fill that feedback link.
So I have just called him. He's on the process of getting logged in. Please, others, can others mute your mic? Yes, Shager came. Shager. Hello, Dr. Shager.
Hello,
Hello, Dr.
Sajin.
Shager.
Yeah, I'm here. I'm here.
You're able
I'm
to hear
sorry.
us?
Yeah, I can hear you. I can hear you.
Yes. Shager, I have given a brief introduction about you, but
Okay.
again,
Doesn't matter.
Dr. Shager Lucas Kuriakos is the member secretary for the Kerala State Disaster Management Authority. In his busy schedule, he was able to log in. And I think, Asha, can you give the co-host to Dr. Shager Lucas Kuriakos?
It's already done, sir.
Okay,
Let's
Shager,
start
now
now.
I have given the introduction about you to all, and you can directly jump into your topic, your keynote address, please, Shager.
Good afternoon, everyone, and thank you, Dr. Sajin and the organizers. And I'm really sorry for this short delay. I was actually not getting connected for some reason. I was thinking that I was already logged in. Now, it's very interesting to see that there is a international geosciences colloquium that's happening over the web, which when I was still pursuing my doctorate, we used to be traveling thousands of kilometers from the Netherlands all the way to Vienna for attending the European Geosciences Union. And therefore, it's very interesting that to understand that we would be able to also pursue such serious discussions over net. This is actually very eco-friendly because we know that we should be consuming less carbon. Having said that, you are also going to listen to my professor, Case Van Westen, soon today, I believe. Hence, I'm not actually going into a lot of technicalities, but I'm actually interested to talk to you mostly about what is needed from the geoscience community for quasi-judicial administrator of disaster management in any part of the world. We must realize that when we pursue a lot of research, we tend to be very focused on solving.
Dr. Shager, your mic is mute now. Your mic is mute.
Oh, I'm sorry. Can you hear me again?
Yes, you are able.
Yeah. So I hope you heard what I was trying to tell. I was telling that, well, in the past, it used to be very difficult to organize such international colloquiums because we had to travel several thousands of kilometers and consume a lot of carbon before we do that. Now, these days it's much more easier, and I could sit in my office and talk to half of the world about what I think of geohazards, its mitigation and management. I'm not going into the technicalities of it, but I'm more keen to talk to you and to orient probably the young researchers herein as to tell you what we who administer disaster management need. It's not often a lot of academic inputs that are required. It is always, and it is most often, that crucial academic input which is required. What is crucial? A general literature or an academic paper that we would write out in our academic pursuit might have a lot of academic value. Definitely it adds to the body of science, and it is no less than any other document that has a legal mandate. But what happens is, when it comes to translating it into governance, into administration, the requirements are not just academic. They anymore are not made purely based on academic inputs. They are based on several other factors that the society is entangled with. This includes the socioeconomic situation in which the society is, the cultural context in which such decisions are made. Unfortunately, we, while pursuing our academic interests, tend to ignore these facts. So what happens when we stand ground with solid academic evidence on a particular fact? If that fact contravenes what is socio-economically and culturally suitable for a particular society, then it becomes very difficult for administrators and policymakers to assimilate it into governance and administrative decisions. For example, we would tend to believe and we would tend to argue from a geosciences perspective that we can't permit people to live in high hazard prone areas, be it landslides or floods. But we must also realize that human beings are human beings because they are the survivors of the fittest. They have withstood, our forefathers have withstood the fury of the world, the earth, since time immemorial to evolve into what we are now. Now, if that is the situation, if Mesopotamian civilization has originated, if Indus Valley civilization has originated in floodplains and have withstood floods, our present day society also has to find ways of withstanding it in a better manner and live with those events. I have come across in my long stint of nearly 10 years now in this quasi statutory position of an administrator of disaster management in the state, people arguing to evict people from high hazard zones, to completely leave such areas pristine for nature. Unfortunately, while they do it with a great lot of good faith and knowledge and academic backing, it cannot be translated into an academic decision, an administrative decision, I'm sorry, because the socio-cultural and the economic situation of those people do not permit it. If they are not permissive for such an action, then the political hierarchy of the state, the political decision makers will never be able to make such a decision. What is an alternative? There are plenty of alternatives. In Kerala, what we did was we instituted a vulnerability linked relocation plan. This is India's first. We started it early in 2017. In 2018, sometime before the major Kerala floods, we had it approved by the government. And now we have about 3,000 people who have taken the benefit of this scheme and have moved to less vulnerable areas. And I, again, put in double quotes, less vulnerable areas of the state from highly vulnerable places. How did this happen? Why did this happen? It's because when we instituted the scheme, we decided that we are not going to resume the land. Why? Culturally, people have an emotional attachment to the land that they inherited from their forefathers, or the first land that I or you bought with a great lot of toiling in life. Hence, if we offset that emotional quotient and take a very pure administrative decision of offering a certain perk and asking them to move out, it would not find any success. Whereas in Kerala, we were able to succeed in the scheme and give out about $1 million Indian rupees per family to move to less vulnerable areas through the scheme, because we never said them to surrender their land. Instead, we said, you can't live there. You can cultivate there, but you cannot live there. You cannot have a structure built there. So this approach towards administration was facilitated by inputs not just from the Geosciences Academia, but also from the social work academia, as well as from the economics domain. Often, we as geoscience practitioners tend to ignore these other domains, they being the sociology part of it, or the economic part of it, or be it the cultural part of it. In this colloquium, when I look at what all domains that you are discussing about, which also relates to disaster management one way or the other, I do see that we have a very strong orientation towards the science of disaster management. But remember, the science of disasters is within the framework of management, and management is never done with just science as input. Having said this, I urge upon all of you, particularly the young researchers, to also have a socio-cultural and economic perspective towards the problems that you tend to analyze in your academic pursuits. Keeping that apart, when it comes to mitigatory solutions, which are palatable and affordable, and I reiterate, affordable to society, will never evolve. Further, I must also tell you, with my long experience in managing crisis here, many of the mitigation solutions that we tend to propose also tend to be very hypothetical. This is primarily because there are no practicing grounds for the young researchers available. I do see, at least in the context of the state, we tend to be more on the desk and less in the field. I doubt, other than the Agriculture University of the state or the Veterinary Sciences University of the state, whether any other university has a field laboratory area permanently monitored and permanently sampled on a regular interval. I urge upon the geosciences community of the state, but at the same time request the support of all our international colleagues to come forward and establish permanent monitoring and investigation patches, geoscience investigation patches or land area in the state, wherein you would be able to continuously investigate, observe, study, experiment with mitigatory solutions, come out with practical estimations, quantity estimations, and solutions for real life problems. We all speak about USLA, we all speak about RUSLA, we all speak about a number of, for example, Manning's equation. All this were experimented in experimental patches of land and developed by continued observation and research by a team, a school of researchers in those areas. We tend to still remain in those equations. Have we looked at it from any other perspective yet? Have we really created patches in the different parts of the world to experiment with these and add to the body of science, and not just science, but also find practical solutions to problems that are faced by disaster managers and offer it as estimations, as project proposals, which can be translated into real life? Hence, when we discuss about geohazards, its mitigation and its management, I believe all our discussions should embody the context, the social, cultural, economic context in which we discuss, and customized, locally experimented solutions developed with practical experimentation in the field. If a project is proposed to an administrator, the administrator looks for a valid proof. If there is no valid proof, then it is only a research experiment. And there are ample number of research experiments that are in the shelves. What we want is, what disaster managers on the ground who are in the forefront of fighting this out needs is real life solutions. While the academic community can continue pursuing the academic pursuits for betterment of the science, there is also a larger requirement from the academia to start providing real, solid, grounded solutions which would facilitate mitigation. With these words, I conclude, and I once again urge upon the young community to think of what I suggested here. These are probably the lamentings of a practitioner of disaster management for quite a long time now. And you are the future. All of you should facilitate all of us with better solutions, better real life solutions, practical solutions, pragmatic solutions. And I look upon this colloquium to come out with good proceedings which would give us pointers and give us clues towards where we should be progressing further in these domains. Dr. Sajin is our advisory committee member in the Landslides advisory committee, and he and Professor Case and Bran IC is also here, would all team up and facilitate us better. It's also interesting that Christ College is here. Christ College Iringalakuda was one of the first to receive research funding from KSDMA sometime in 2016 or 17, if I remember. And we will continue fostering collaborations with academia. We will continue facilitating research projects as we have always been trying to do. But I urge upon again, please bring out practical, pragmatic solutions. With these words, I thank all the organizers and particularly my good friend, Dr. Sajin, and everyone, every organizer here for having me to speak to you. Thank you.
Thank you very much, Dr. Shekhar, for your talk, or rather a keynote address. But we wish actually we have another 25 minutes to go for the next talk. We wish, being a member secretary for the Kerala State Disaster Management Authority, can you explain a few examples how you handle the 2018 anomalous rainfall and its associated natural hazards? Everyone will be curious to know a few examples.
Thank you, Sajin. I tend to speak less now and listen Yeah, thanks for pondering my head with how 2018 floods were handled. Yes. Uh, if you look at 2018 floods, it was until August 8th that we didn't have a solid, reliable warning which said that these are the places where the rains are going to be extreme. But if you look at what was coming in before what came out and evolved into a century's biggest flood event in Kerala, there were this classic meteorological outputs which said there'll be heavy rains and we expect that the rains will be there from this day to that day. This is often how meteorologists are able to do it, and that's nothing wrong with them. It's where the science is yet. Having said that, it was on 7th of July, I guess, that in the middle of the night I got a call from Wayanad telling me that there were landslide events being reported and that there was heavy rainfall. Listening to this, immediately we pressed in the National Disaster Response Force teams, which were already pre-positioned in the state. Because here in the state, all preparedness for monsoon starts sometime in May, the month of May. There's a very nice documentation of series of inputs. And based on that, unlike in 2017, we had come out with an SOP which was much more broader, much more wider, and had more facilitation in there as to telling what has to be done. As part of that, we already had an agreement with Army, Navy, Air Force, and NDRF to deploy them in large numbers if the need was there. So the need was felt on a particular day in the middle of the night at 2 o'clock, and then we started responding to it. In the first day, it was confined to Wayanad. In the first spell, it was confined to the north of Kerala. We had some amount of rainfall happening in the north. And then slowly, when August emerged, we saw that it was coming down to the south of Kerala or in the central part of Kerala. Now, when this was evolving, equally, we were working 24/7 in the state EOC to facilitate more and more research and more response systems. So eventually by August 5th, before the real big spell happened on 15th of August, we already had 56 teams of NDRF, 22 teams of Indian Army, and for the first time, Indian Army even deployed special ops teams, whom you would have all heard from the surgical strike operations here in Kerala. I was the first one to deploy them in any civilian operations. So we requested their service. We had, for the first time, BSF operating amphibian patrol vehicles in a civilian response. They use it very extensively in parts of Gujarat, but in Kerala, it was very new. We knew that this asset existed. We requested for it, and they facilitated it. So eventually, this was Century's largest operations. But what was very interesting was how the community responded to it, and that's what I would like to tell. When we look at any catastrophic events, and as you know, in 2018 was not a bad year for the rest of the world. It was for Japan. In Japan, we had in the same time when Kerala was being flooded and hit by landslides, Japan had a severe such spell which killed 260 people. And often we hear that when such major calamities come up, people say, oh, there is inadequacy of equipment. Oh, there is inadequacy of that. You haven't done this. But if that was the case, then why did Japan also have so much of fatality? 260 deaths in a day, and that too in a country like Japan? Well, quite surprising. So this brings we disaster managers to the very simple point that there is nothing called adequacy in disaster response. You will always be in want. If there is a catastrophe, there is no equipment that is going to solve your problems. Who will solve your problems? The first responders. Who are those first responders? Our own people. NDRF will take at least a couple of days to reach. Army will require a couple of days to be mobilized. We started early, so we had large numbers by August. But if we don't start early, what will happen? We will not have sufficient numbers. But even if you have sufficient numbers, are they sufficient? In Kerala, 36 lakh people were affected by the floods of 2018. That is roughly about 3.6 million people. However, the response was so swift. And why was it so? It was because the local community responded. An example and an epitome of response by local community is evident from how our fishermen community responded to it. So it became a saying and a statement even in the World Reconstruction Conference and the UN DRR conference that when the world has Superman, Kerala has fishermen. And that's where we went. How did this happen? Did it happen overnight? Is it because that suddenly we disaster managers had that big halo telling us, well, let's mobilize fishermen and let's start doing this community response? No. Don't be misunderstood. That's why. It happened because of three things that the state is very proud and unique about. Number one, we have free and universal education. Our society is very strong in its educational levels. Two, we have free and universal healthcare. This again is nothing new. It's there since time immemorial. Our forefathers invested in it. And the third, and this is where management comes in place, and the third and the most important is local self-governance. India's best local self-governance is in Kerala. We have local governments who were the leaders of response. They stood ground. They knew what they were doing. They had educated people there. These educated people came together, healthy people came together and responded to it. So that's what happened. So if you ask me, what was my role? Well, my role is to manage the State Emergency Operations Center and deploy people, deploy assets, deploy resources. But it's not me or anybody who did the wonder. The wonder is by the people. And that's why when we went to the World Reconstruction Conference or the UN DRR conference, everywhere the community response of Kerala was upheld. Everywhere it is what was kind of told as a story. So what would I, as an administrator of disaster management, do if I have plenty of money to increase the resilience of my population? The answer is simple. Invest more in education, invest more in healthcare, and strengthen our local self-governments. This is all what you got to do. So Sajin was asking me what to enlighten you with what I did. Well, I didn't do much. I didn't have to do anything. I was standing on the shoulders of giants. The society itself is full of giants. They did the job. We just had to ensure that there is a leadership for all that. And our honorable chairman, who is also the chief minister of the state, stood ground, took the leadership, led the entire society. And it's telltale now everywhere. He said, let's walk, let's begin. And everybody stood ground. That's all what happened. The nice stories of resilience, nice stories of what happened during the floods. In 2019, again, we saw flood. But in all these instances, who responded? Who was that crucial responder. That was the society. A highly educated, a healthy society which had local leadership and a collective leadership. So I reiterate, in a disaster of an L3 magnitude like what Kerala faced in 2018 or 19, there is never, ever an adequacy of resource to respond. If you believe that there is one country which has all the adequacy in the world to respond to any catastrophic disasters, as we see in the famous Hollywood movies, even the US is crumbling before what is happening in California. It's not just a forest fire, it's an environmental disaster. The world is going to suffer for that, what happened in California. It's not just US, it'll be the entire world. That's the magnitude of that event. There is no adequacy. It's not that the emergency responders there are not doing anything. They are trying their best. They're flying into the fire. But no, there's nothing called adequacy there. What is adequately available? Human will. For human will to prevail, for collectivism to prevail, you need to provide that society with good education, good healthcare, and local leadership. These three are ensured in Kerala. So practically, the job of disaster management in Kerala is much, much simpler than anywhere in this country. It's only to give them adequate orientation. We stand on the shoulders of giants, and our own societies are giants. So, Sajin, that's how I would put it. I wouldn't say anything more about it.
Yes, actually, Dr. Shekhar, there is a question for you in the chat box. If you could answer that one, that would be better.
Dr. Saju, actually, we are now facilitating. I already told you that we have a vulnerability linked relocation plan. I will send you the link of that just now so that you know what's happening with that. It's a large mitigation project that's ongoing. This is running for 2018 and 2019. The report is being posted here. But beyond that, we are now experimenting with 3 different landslide warning systems. As you know, landslide warning systems are not foolproof anywhere in the world. And we are trying to support Dr. Sajin and his team. I think they are working on creating a landslide early warning system in there. Professor Thomas is also part of that team. I think he's leading it. We also have another project which is funded under the Kerala Infrastructure Fund Development Board, which is by a satellite, a small satellite, a nano satellite company called Orbital Solutions, where we are attempting to utilize nano low-flying small satellites for landslide early warning. There's a third project we are just triggering with Geological Survey of India to experiment what they are presently doing in another state, as to experiment it in a part of Kerala. So there are 3 landslide warning projects that are also in the offering. If you look at these 2 links that I've given, the reports are yet to come there, but therein you will actually see the government order and what we actually do with the vulnerability linked relocation plan. We have about 3,000 people who have taken that and moved out of landslide prone areas. Their housing, they have moved out, and they still keep the land for cultivation. So we don't know severe their what do you call their emotional attachment to the land. But if you look at other precautionary measures, Kerala is very densely populated. You know it. We all live here. With this number of people, we can't tell them to move out just like that. It's a governance dilemma that we all have. Nothing else will actually work. In 2019, we sent out 50 teams of geologists and soil conservation specialists across the state, identified locations wherein people live who has to move out of those areas. And this list runs to about 6,000, 7,000 individual dwelling units. And this has been communicated to those families. Some of them have willingly taken this vulnerability linked relocation plan, but not all of them because of the emotional part of it. But as you can see, when such a large investigation happens, we tend to end up having these big numbers. You can also see those maps in our website, where you will see that these people are from where they have to move out. I will be posting it subsequently to Dr. Sajan, so he can actually share it with you. So we have all of this in a geospatial environment here. We have a DSS wherein this is fed, and there you can actually see that. So yeah, slope management. There is another question. Sajan, can I continue with these questions?
Sure. You have 10 more minutes.
Okay, thank you. What are your views on the need of the dedicated slope management system in the country? It's a wish for a geoscientist to say that in slopes greater than 20 meters don't have any construction. But in Kerala, it's not feasible. That's the fact, Mr. Kishore. Whatever we try, the moment you start touching those little portions of land, I think we will end up triggering or creating conducive conditions for events in the future. So I don't think that in places like Kerala, the solution is that we have a slope management system. If you go to many of these landslide affected areas, you see that a lot of those places are thickly vegetated, you know. But if you tell that there has to be structural interventions before a middle class or a lower middle class person in the state starts constructing a house, I don't think that it is affordable for the society. However, from SDMA, we have issued a checklist to the government saying that when people start constructing in hilly areas, they have to follow this. That's presently under the consideration of the government. And if the local self-government agrees to it, then at least there will be a prudent examination of the slope before they start cutting and filling to construct houses. What are your experience with negative practices in development activities and agriculture in Kerala contributing to landslides? Anto, interestingly, agri is a culture and it's long practiced. For example, if you look at what happened in Malappuram in 2019, where a large landslide occurred, upslope, you would have heard that they were replanting rubber. But if you go and examine those rubber pits, the pits were built in the prescribed depth and width as prescribed by the National Rubber Board. It's since 2010, when I think even before that, when me and Sajin were still students, National Center for Earth Science Studies had issued clear instructions across the state and spread it across the state, saying that please don't have such pits, water holding pits in such slopes when or just before the monsoons begin. But then the agriculture practice demands that there has to be pits dug then so that planting can be done properly and that the saplings will grow well. Unfortunately, what happens is that these practices are practiced by farmers, poor soil bread earners. They have no other method to plant. So if we can devise other methods to plant rubber or whatever cash crop that they want to plant within the small holding that they have. And you must remember in Kerala, the land holding is less than 1 acre, and that's the lowest in the country. So if that is the case, we will have to be very careful when we point fingers at agriculture. Now comes the question of development. This has long been debated. I hope you would have also seen me myself quoting in some frontline media about the tarmacking of roads and the need for so many roads in Kerala, the density of road network. It's not that I don't want roads, but do we have the economic depth in our pockets to afford better roads? I don't think so. We don't have. And we can't tell people living in the hilly areas or in the remote part of the state that, well, we will go by a tarmac road. You don't go by those. You live there as if that you are dwellers of this land in the pristine times of forest. No, we can't do that. That's where I said in the beginning that it cannot be just geoscience academic know-how that governs administration. We have to cater to the needs of those families who live in such areas. So if you just generalize everything into development activities, then I have this counter questions to you. But if you ask me whether you want a road in front of your house, which is tarmac and well built, you would definitely say you want it. And to build such good roads, you need quarries. And whether you want a quarry in your doorstep, no, you will not agree to it. That is called governance dilemma. We have it very well in Kerala. We are environmental friendly when it suits us. But then, unfortunately, when you are managing governance, your decisions cannot be that blind. It cannot be just focusing on that. We have to balance between what is needed by the policymakers, what is needed by the community, and what the higher administrators would look at. So these issues have to be thought in a broader perspective of management. You cannot do it just with geoscience perspective and geoscience facts, you know. Those facts should guide all of us with practical solutions, but we cannot take decisions only based on that. I hope I've answered. Yeah, and I think Kishore is not asking a question anymore. He's just making a statement. I hope he doesn't want me to react to it. Well, I would really wish that there be a proper slope management policy and concept. Yeah, from my geoscience heart, yes, I would love to have it, but I'm not sure whether that's really practical in a densely populated state like Kerala. So thank you. It was a pleasure interacting with all of you. That's why I keep my talks less and try to talk to you all. Thanks, Sajjan. It was really great.
Okay, Dr. Shekhar, thank you very much. I know you are so busy and sparing about 50 minutes for us. I think Dr. Linto Alapad, he is assistant professor in Christ College. He is the chief organizer of this program. I wish, Linto, you can say a few words for concluding this talk. Your mic is...
Hello, yeah. Thank you, Dr. Sajjan, for this opportunity. It was really nice to listen to Dr. Shekhar Lucas Kuriakos. Certainly, it was very important in sense of Kerala, and we have the best person with us today to speak about different aspects of geohazards in the state of Kerala. So thank you so much. Though, like I also had some questions in my mind. Probably I'll ask maybe in the next opportunity that may come in the future, because we have this time constraint now, so we should finish. So thank you so much on behalf of all the participants, the organizing committee. Thank you, sir. Thank you for your valuable contribution. And it indeed is a very important occasion that you have agreed to come with us. I mean, to appear here in this geoscience colloquium, because we have many students attending this. And I remember that there were many special requests, especially for this session. They wanted to attend in this session because of the importance of this geohazards. So thank you so much for your presence, sir. Thank you very much.
Thank you, Lindu. Thank you, Sajin. Thank you.
Okay, thank you very much.
I'll be
Actually,
in the background. I would like to listen to Brian, Thomas, and Case. So,
okay.
I'll be around.
Sure.
Listening.
And you see the importance what Linda have told for this section is awards, and the testimony for that is 83 participants are attending this one, and this is aired or streamlined through YouTube also. So there are so many viewers for that one. So thank you once again. Thank you very much, Dr. Shekhar. And next speaker is very much ready. He is Professor Brian Mccarron. He is actually professor in the Yale NUS College in Singapore. The positive aspect of the 2018 flood and landslides is I got several connections across the globe, because Brian is one person who have visited Kerala to study the 2018 floods. So don't think that I am favoring floods and landslides. Rather, I got acquainted with so many personalities like Brian. And the other beauty is that within the couple of years, we are going to publish our third paper. 2 are already published and one is in this pipeline. And I will briefly say a few words about Brian Mccarron. He took his undergraduate from Duke University, Durham, then graduation from University of Otago in New Zealand, and of course PhD from one of the best universities in the world, that is UOC, University of California in Santa Cruz, USA. And he has several, if you are saying about the employment history, he has worked in several institutions, but what envy me and every other geologist is that, which are the journals which you aims at to publish your manuscripts? Science, Nature, Nature Geosciences, Earth Science Reviews, Basin Research. You can see in the Google Scholar of Brian Mccarron, all those journals are listed very beautifully. He has several publications. I think he's teaching in an undergraduate college, but he still maintains the momentum of publishing and doing the research. First of all, I thank you for welcoming Brian Mccarron. I sincerely thank you for accepting my request to words and deliver a talk on this one. Please, Brian Mccarron, you can continue with your talk. Your mic is mute. Your mic is mute.
Not anymore. Thank you for your very kind invitation to this conference. This is quite an honor to be invited here in the presence of people who've done a lot more work on this stuff than I have. Dr. Shekhar taught me a lot when we were down there in Kerala 2 years ago now. I'm also with you, Dr. Sajjan Kumar. I appreciate your tutelage and as much as I can possibly learn from you. Also, on the panel, we have my old friend Thomas Uman, who I haven't seen in some time, but I look forward to catching up with again soon. And also Dr. Case, of course, Case Van Westen, who has mentored so many excellent geoscientists that are really changing the landscape throughout India, and I think really going to end up saving a lot of lives and a lot of loss of property and money. Also, I wanted to, as I start working on getting my sharing my slides here, I wanted to also thank Dr. Shekhar for, which I couldn't possibly ask for a better introduction for what it is I want to talk about today. His comments on two things really struck me, two lists of things. One, he mentioned the need for geosciences to work both in terms of the social and cultural context, which I couldn't agree with more. And although I am very much an academician, I'm not so much a practitioner. What I hope to do is train a new generation of students to think exactly along those lines. I couldn't have asked for a better introduction. We need to teach students of geoscience to think about what do the implications have for considering culture and sociology, economics, all these things in terms of reducing the risk from these disasters. The second thing I want to mention, following on Dr. Kumar's address, Dr. Shekhar's address, is the absolute need for universal education, universal healthcare, and strong governance. These things are three things that are severely lacking in places like California, and I believe that they're actually adding to the risk that's being posed in those regions. So thank you again for the introductions, everybody. It was tremendous. Couldn't ask for a better introduction. Forgive me as I click on some things here because there are people joining from the waiting room, and since I'm the co-host now, I'll be occasionally letting people in. Okay, what I want to talk about today is this idea of kind of a new fancy word that many of us heard, I think is often misused, called transdisciplinarity, or transdisciplinary approaches to understanding disasters in the Asia Pacific region. I changed my title slightly because I realized I wanted to show a couple of examples from the Pacific where we were working also. And as Dr. Sejan mentions, I'm presently at Yale and US College. I'm a professor and the head of the environmental studies program, but I'll be transferring to Duke University in the next academic year, where I'll hopefully be able to actually expand my efforts in Asia, working with excellent people like everybody assembled here. What I'd like to consider now is introducing a model of thinking about different way of thinking about disasters. And this is a very integrated model where we consider the geohazards that are impacting everywhere around the world. And these can often be combinations of geohazards. For example, what we felt in Kerala 2 years ago, last year, and I'm certain this year with the flooding and landslides, was kind of a combination of climate and mass movements. And to understand how those disasters unfold from a geoscience perspective, we want to think about, need to know a little bit about climate, and we need to know a little bit about mass movements. We bring them together. We can start creating understanding of that. Well, at the same time, also as Shekhar mentions, we have the necessity of considering how do these different hazards interact with both human systems and ecosystems. In places in Asia and Asia Pacific region, so many of the humans actually rely on ecosystems for their everyday survival. So to understand those systems, you have to know a little bit about climate, a little bit about mass movements, a little about the social systems that are involved there, plus the ecosystems that those human systems rely on, and how climate is also affecting ecosystems in this time of the Anthropocene. Now, the thing that Shekhar mentioned, which is actually critical in this, are actually working towards solutions. And this is kind of where me as an undergraduate professor stops, and a lot of academics stop. We're not so good at solving problems. We are really good at helping provide the information that problem solvers need. But if you're considering solving problems, I think about this in two different ways. You can either create a policy that affects people's behavior, or you can build something that will make them safe in the face of disasters. And that includes both policy solutions and engineering. I'm going to follow up on this later, but this is kind of a way of introduction to what I want to talk about today. And then we'll go into some examples, and we'll kind of wrap it up, coming back to this idea of this, what I call a transdisciplinary model of disaster risk reduction. The deal with transdisciplinary and the major difference is, and I think both Shekhar and his whole team at the KSDMA would appreciate, is that it goes beyond the academic knowledge and actually involves practitioners and, dare I say, people who are actually impacted by these hazards. We design programs, we design solutions. The best way we're going to get to those is by involving everybody from the academicians in our ivory towers to the disaster managers who know how to deal with this stuff on a daily or annual basis, but also the people who live with it every day. And this is really a hard thing for academics to accept, but I think it's the only way we can move forward to actually reducing the risk for disasters. Dr. Sajan mentioned nicely also that I am at Yale and US College in Singapore presently, and this is a liberal arts and sciences college. This is something that's a little bit different model than what many people in Asia are used to, because many of our universities are modeled after the British system. But what we're doing here is something a little bit different. We're considering different approaches to understanding academia, and all of our students are meant to take courses in both in the humanities and the social sciences and in the sciences. And then they pick majors like anybody else does in either life sciences, math, computer science, and statistics, or physical sciences. These are the majors we have. We only have these 14 majors. We also have 3 interdisciplinary majors: environmental studies, which is my department, global affairs, and urban studies, which bring 1 or more of these, or bring 2 or more of these traditional disciplines together. So for example, in environmental studies, we cover everything from literature to philosophy, certainly economics, the psychology of things like climate change and anthropology is buried in there. We also need to understand a little bit about life sciences and ecosystems and ecology and physical sciences, certainly when it comes to the geophysical systems that are causing a lot of these problems that people like Shekhar need to deal with. Another thing about Yale and US College, which is quite unique, is one, we have access to places like Gunung Palung National Park in Borneo, but we're also a very international school. Now, our students are we only have 1,000 students through 4 years of their undergraduate education. They get a bachelor's degree in science or in arts. But this example from my class that I was able to take to Borneo, we have many different nationalities represented. So about half of our students are from Singapore, and the other half come from 70 or 75 different countries at this point. Now, what that does, it brings a whole variety of perspectives to the table. When we look at problem solving, you can't just do it from any one perspective, but it's really helpful to bring people from the UK, from Sri Lanka, from India, from, in this case, Colombia and Japan and Indonesia and China and Malaysia and Singapore and the United States together to really start working on the best way to solve these problems, like in this case, deforestation and land use change in Borneo. So think about elements of looking at problem solving in this case, having a diversity of perspectives, national perspectives, ethnic perspectives, religious perspectives, economic perspectives is absolutely critical. I'm going to present a series of facts, I think, or things that are arguable in this talk. And the first of which is the truism that we are indeed damaging the very systems that keep us alive. Now, we think about climate change as being an easy one, but we're also affecting our oceans and we're affecting our landscapes. Certainly with atmospheric change, we're seeing larger tropical cyclones affecting places all over the world. We're seeing climate change, changes in rainfall patterns, certainly changes in the monsoon. Indian Ocean dipole event is causing all kinds of problems in the Asia Pacific region, or mostly in the Indian Ocean region. Clearly, the atmosphere, the impacts that humans are having on the atmosphere are making it a lot more challenging for certainly the most vulnerable of us to survive. The changes in the oceans we're having with ocean acidification, ocean warming, ocean pollution, as you see in this example from Indonesia. It's really quite remarkable how this key system that provides something like even 50% of the protein sources that we have here in Singapore from fish consumption are being damaged by humans. Without this resource, humans are going to suffer certainly for lack of protein. Freshwater resources, the amount of pollution, the damage that we're doing with landscape change and erosion of different things, pesticide, herbicide use, and industrial pollution are damaging our freshwater systems. And of course, this is the one thing that we absolutely need to survive as humanity that we're damaging. And finally, the air, separate from the atmosphere. Think about air pollution. You look at this image here, which is from Indonesia. The land use change and fires associated with deforestation associated with palm oil development is a very complicated dance that people have to do because, one, they have the right to develop and seek better livelihoods for themselves, their children's education, healthcare, fresh food, fresh water, all these things that everybody wants. And to do that, you need to consider development in this current globalized world of capitalism and whatnot. And going further past this, and I question to call this an actual planetary change, but if you look at the scale of landscape change that exists in places like Haiti, which you see in the background here, it's really quite tremendous to see how humans are truly impacting landscapes at a really almost global scale. The erosion that comes from Haiti and the loss of topsoil is causing all kinds of food security issues, let alone choking of rivers, impacting offshore ecosystems, fisheries, and everything down the chain. So it's not a surprise, perhaps, that the Earth is indeed trying to get back at us. They're trying to kill us. It's almost like we're a virus and they're trying to get rid of us. We can look at the disasters we've had recently. As mentioned before, these unprecedented fires in California. We can look at very recent events. This was just 2 weeks ago in Vietnam, where landslides killed upwards of 100 people, I believe, in this last iteration. And we're getting to the point in East Africa where the plagues of locusts remind us of biblical times, where these hordes of locusts descend and eat the same equivalent of, in one day, of a city of 35 million people. This is unprecedented change we're dealing with in our climate, and the Earth is actually fighting back and saying, hey, we need to adjust or else the Earth is going to perhaps adjust for us. And of course, despite their cuteness in this particular image, the intersection between wildlife and humans, interaction between wildlife and humans these days is increasing as these landscape changes continue to occur. And things like bats are becoming increasingly interacting with us and our wildlife and our also our agriculture and our livestock, causing things like coronavirus outbreaks like we're going through right now in the world. So here in the Asia Pacific region, we are really at ground zero for a lot of the hazards that impact us. We have floods, we have droughts, we have heat waves, not so many cold snaps, thank goodness. We have tropical cyclones and typhoons, we have hurricanes, sorry, not hurricanes, we have typhoons, we have volcanoes, we have earthquakes and tsunamis. We have it all, we have fire. Everything happens in the Asia Pacific region. Now, because we're surrounded by so many hazards here in the Asia Pacific region, I think it's also critical that we define risk as a way of addressing these problems. Now, Dr. Shekhar mentioned also that oftentimes these conversations around disaster risk reduction are dominated by natural scientists. We need to get past that, and we also need to incorporate in this risk framework the work that many people do at the intersection of risk with these geohazards that so many of us are scientists deal with. Now, our role as geoscientists is very critical in this conversation, but it's also reasonably well defined. In my opinion, and I could take some argument on this, I happily do this, our job is quite very simple. It's important we understand the basic physics behind the hazards we're looking at. We need to know how earthquakes, landslides, monsoon seasons, atmospheric circulation work. These are absolutely critical to understanding to then get to the next level of what are the frequency and magnitude. Now, a guy like Shekhar, any planner, any family who's making a decision wants to know, if we're exposed to a hazard, how frequent is this hazard going to happen? And when it happens, how big is it going to be? As geoscientists, that's our main role. That's one of our primary roles. Now, also mixed in there is this idea of uncertainty. We can't say, yes, there's definitely going to be a magnitude 7.6 earthquake that happens every 23 years. We have to be able to communicate uncertainty, and that's the real challenge we're having, certainly with this current trying to explain the current phase of climate change we're going through. Now, risk happens at the intersection of these geohazards, these hazards the Earth planet throws at us, and vulnerabilities. Now, these vulnerabilities are stuff basically that can break. And when we talk about things breaking, that includes ecosystems, people, certainly communities, and even sometimes full societies. We see sometimes if there's not an adequate response to a disaster, entire government can collapse actually. Also, buildings and infrastructure can be vulnerable, but these are things that they're really outside the realm of geosciences and have to deal with certainly life sciences, social sciences, anthropology, psychology, engineering. Civil engineering is a big deal, structural engineering, but also the idea of politics, political science, and government studies have to come in there. These are conversations that's at solutions that'll actually start saving these lives and saving loss of property also. I got into this line of work not long after the big Indian Ocean tsunami in 2004. And our goal, we started off doing with this, was going to these areas and finding evidence of old tsunamis. This is our colleague from Thailand. And you can see here many different layers, I think at least four different layers of tsunami sand that have been deposited in this marsh in Thailand. Big they are. Dr. Sajjan mentioned very nicely that we had a publication in Nature a few years back. We were able to find some of the evidence of the last tsunamis that happened before the big one that happened in Indonesia throughout the Indian Ocean in 2004. What we were able to do was go through into Aceh province, and we were able to dig in some marshes, and we found this beach ridge sequence where the deposits were kind of caught in the swales in between these beach ridges. And we found an interesting pattern that exists where the oldest deposits were furthest inland, and they got younger as we went closer to the modern day coast. And the 2004 tsunami actually covered the entire distance. We were able to use carbon-14 dating to get the frequency of these events, which you can see pretty clearly there. But when we get to magnitude, that's a bit of a different story. Now, it might be tempting to think that the biggest tsunami would have been that 850 because it went the furthest inland. But the other thing we don't fully understand at this point is the evolution of these beach ridges. So our next project went through and worked on some models for figuring out what is the frequency of this beach ridge related to, and it's got to do with a combination of earthquake cycle and sea level change. But I started asking the question also, now that we're fully in the Anthropocene, how is human impact affecting something like beach ridge sedimentation? You look at sedimentation changes in a place like Haiti after 200 or 300 years of deforestation has come. There's been a lot of sediment, a lot of erosion, a lot of sediment deposited in the coastal zone. I started wondering if the same thing would be happening in Aceh that could actually affect this beach ridge progradation. We didn't get that far in the study, but for one thing, Aceh, for a number of reasons, has not had that much deforestation. You can see here in the northern part of Aceh where the tsunami, northern part of Sumatra, the tsunami hit, there's been pockets of deforestation, but it hasn't been like the widespread deforestation you see in the lowlands of Sumatra over here. Like different kind of look at it from Global Forest Watch does show, however, a fair bit of deforestation, historical deforestation in the area that was largely impacted by the tsunami, and the area we were working with the beach ridges is right in here. So you can see some significant deforestation. And I think it's important to understand what are the impacts of humans deforesting the landscape that would affect the sediment regime in this area. If we're only looking at it from a geologic perspective, we're going to miss that, and that could be a big clue to understanding how this landscape evolves. Now, we had a lot of discussion about this in my lab here at Yale and US and at various different places, but I still argue, even as an American, that people are not stupid. People, when they can, make good decisions, they make informed decisions, ideally. They're not going to put themselves in harm's way. However, when you see things like the 2004, oh yeah, sometimes, however, some people are indeed, you might question their intelligence. It's not the bear's fault in this particular image. But you might question the judgment of an entire city like Banda Aceh occupying which were historically intertidal wetlands in an area where they're known to have large earthquakes. Now, the known to have large earthquakes is somewhat debatable considering the last big earthquake to impact this area was over 100 years prior, and prior to that would have been 600 years before that. So memory can come and go, but these people made a very informed decision. They looked at the economic benefit of living in the coastal zone and all the ecosystem services that come with that and said, you know what, chances of me getting a good livelihood and a good source of food for my family and living with a good community, I'm going to enjoy those benefits from living in this area and risk the case that we might have a once in 600 year tsunami. That's an informed decision. These people are not in my opinion, stupid. The other thing we've been exploring in our research is the role of indigenous knowledge. This is particularly important in places in Asia Pacific because there's a lot of people that have a lot of memory here and they know things that we don't. So my fifth assumption here is in some cases, despite all of our fancy degrees from University of California and University of Twente, these people may know the more than we do. This young woman, in fact, saved the life of her family here during the 2004 earthquake. Now, 2004 epicenter of the 2004 earthquake was just here offshore Banda Aceh. This is a magnitude 9.2 earthquake. It caused up to 3 meters of uplift in the northern part of Pulau Simeulue, a Simeulue island here, and created a massive tsunami that we're all aware of, killed over 250,000 people throughout the Indian Ocean basin. Now, this woman and her family lived on Simeulue Island. They were about 30 kilometers outside of the epicenter of a magnitude 9.2 earthquake. And during this event, the entire population of Simeulue, about 80,000 people, there were exactly seven people that died during the 2004 tsunami compared to over 100,000 in Banda Aceh proper. Why did that happen? How did that happen? If we're in the business of reducing risk from disasters, we want to save lives, we best understand the different tools we have available. Now, this is the village where that young woman and her family lived. You can see they lived in a very modest house right here, and the house was destroyed, unfortunately, during the tsunami. But she recalled a story that her grandmother told her about a wedding party that was on the beach about 100 years prior when a massive earthquake hit. The earthquake hit, and a tsunami came in and wiped out the entire village and killed almost everybody there. So she remembered that story that her grandmother told her when she was a little girl. So when the earthquake hit, she took her family and simply walked up the hill to a prearranged meeting place in the high ground. If you look at this place, they met there, the whole village met there, and actually some other villages who were in the coastal zone also met there. They had prearranged meeting place here. They actually had bamboo structures set up. All they had to do really was throw some tarps over that and over the bamboo structures, and they could set up pretty much a makeshift temporary village in the meantime. By the time we got there, about 3 weeks after the earthquake, they had schools set up, they had food stalls set up. They're pretty much running almost business as usual, and 0 people in this community died in the earthquake or the tsunami. This is a remarkable tale of both resilience and planning. They knew this was a risk they were facing. Take you to another example where we had indigenous knowledge save a bunch of lives, and this was from the Solomon Islands a few years back. And we consider indigenous knowledge. First of all, here's the location map of where the Solomon Islands are. A very remote set of islands, archipelago on the subduction zone here. And there was a magnitude 8.1 earthquake on the 1st of April in 2007. Generated a pretty significant tsunami. It was 8 to 10 meters in certain places and killed, I think, about 50 or 60 people in this group of islands around Gizo in the western province of the Solomon Islands. However, we're going to zoom in here on the capital island here. Interestingly, there are 2 populations that lived in Gizo at the time. There was an indigenous population represented by Bradley, the tall guy here on the left-hand side. Bradley is Melanesian, clearly, and he is part of the indigenous population. There's also an immigrant population that came from the atoll state of Kiribati. Kiribati is far away from any subduction zone, and they had been there for about 50 years at this time. They had to leave Kiribati because of a climate emergency where they started running out of water, so they were relocated throughout the South Pacific region. Well, it turns out that the group from Kiribati, the Kiribati people, these ethnically Polynesian people, were settled in this village called New Manra, which is very close to the administrative center of Gizo. And the administrative officials there wanted to be able to keep an eye on them, make sure they were adjusting okay to life in the Solomon Islands. Where the indigenous population lived out here in Pailangi. And at Pailangi is where Bradley and his family lived. Now, these are very similar physiography. They both had a reef in front of them for a possible buffer against a tsunami. They both had channels you can see here where they can get boats out and fresh water would come down from the hills in these areas. So these are 2 areas that are very similar physiography. However, we actually looked at the demographics of these areas. It turns out that only 20% of the population of Gizo is immigrant, yet the deaths represented over 60% of the deaths. And the story here is what happened in many places. You can see Pailangi here at the top. When the earthquake happened, Bradley and his elders in his village grabbed the older people and the younger people, the most vulnerable in the community, and they simply went into the bush. When the tsunami, the earthquake hit New Manra, as we hear oftentimes, the water rushes out of the lagoon. The children go into the lagoon to check out the fish flopping around on the coral reef, which they'd never seen before. The parents go down to get the children so they don't get in trouble. The tsunami comes in and kills a bunch of people, unfortunately. So that's the story, again, where indigenous knowledge managed to save a bunch of people's lives in the indigenous population there, but unfortunately it didn't work so well for the immigrant population. Another example that I want to use, and this is the example I have from Asia, another example from Asia. This is from a little bit north of you in Indian, from Nepal. That yes, where it's important to understand the vulnerabilities and the indigenous knowledge in these sort of social systems, the climate does matter also. I don't mean to downplay that. This is an image of a village in the background here in Nepal that's being abandoned because of climate change, or at least that's the story that we were told. New York Times picked up on this not long ago, just earlier this year. They did a whole story. They sent a photographer of this village and said, yep, this village is being abandoned because of climate change. So we were there last year before the New York Times was, and want to check it out. Now, we think about climate change and how it impacts people, and this is what's important. So you consider there's increased greenhouse gases. We know this story, and this is the case in Nepal. That can cause increased temperatures, can cause rainfall variability. Over the course of a year, we might have about the same amount of rainfall, but it could also just be coming in more frequent downpours and more massive downpours, like people in Kerala know, certainly. And that comes in the form of extreme weather. We're not going to worry about the ocean side of things because these villages are about 4,000 meters above sea level, so that's not so important. Certainly, when you're dealing with trying to live at 4,000 meters above sea level, you have things like altered crop yields with warmer temperatures, reduced rainfall, these things. Even the nutrient content of the food can go down. And of course, when the stresses in the environment cause a decrease in supply, the demand goes up and prices increase. And that can actually affect people's ability to get the right kind of nutrition and to actually survive. So we took a journey. We went from, this wrong way. We went from Kathmandu and we flew to the city of Pokhara. And then from Pokhara, we took a very bumpy 2-day Jeep ride to a place called Jomsom. And then from Jomsom, we walked for 5 days to the village of Lomantang in Upper Mustang, up by the Tibetan border. By this time, we're getting acclimated to the elevation. And then from Lomantang, we took by horseback, about a 3 or 4 hour horseback ride to the town, of, let's forget the names. Samjong was the name of the village we went to. Now, I always tell my students, my undergraduate students, that science is indeed a social enterprise. And we end up meeting this guy here, whose name is Tashi Gurung. And Tashi Gurung is from Lomantang, and it's a very small village, maybe 500 people. And he speaks the local languages. He speaks Tibetan plus the local dialect. And it so happens, as we were maybe drinking a beer or two at night, after a festival we were visiting, turns out we learned that he's a PhD student at Arizona State University studying the impacts of climate change on tourism in Nepal. And it turns out he had never been to this other village that was meant to be abandoned because of climate change. So of course we invited him along, which was a really, really fortuitous meeting we had there. Now the road to Samjong, you can see Lomantang here in the background, involved going over a pass. It was about 4,500 meter high pass. And you can actually see a clue to what's going on here as you see this road being carved up and over this pass. Now, when we got to the pass, we looked over the other side, we saw this rather remarkable looking moonscape. And I think the engineers quickly realized that putting a vehicle road down through this landscape would have been rather daunting and rather challenging. But you can see down here the track we were going to follow by foot for the next, or on horseback for the next few hours. One of the clues we saw as we were going up the riverbed, and this is the headwaters of the mighty Kaligandaki River, was salt in the riverbed. And anybody who knows anything about agriculture realizes that this degree of salt in the water cannot be any good for crops. And this is exactly the kind of stress that stress crops, their ability to actually grow the amount of crops, but also affects the nutrition in this area. So we're walking up this riverbed in this very desolate landscape. And then we pop over a little ridge and we come into this gorgeous valley about 4,200 meters above sea level. You can see fields that have been early planted here with grasses. You can see horses and goats foraging on this grass. And it was really quite a beautiful place. You can understand why people want to live here. We get to the village, and much to our surprise, it looked anything but abandoned. It was a very tidy little village. There were a bunch of very young kid goats here. So it seemed like people were really making an investment to stay in this village. And if you notice these caves up above, these are traditional sky burial caves. And it turns out that this village has been occupied for over 3,000 years. And after 3,000 years, we learned from the archaeologists and the anthropologists, they're talking about abandoning this village because of the changes we're going through in climate. Well, we start walking through the village on our horses, and this old woman pops out and she says, "Hey," and she's talking to Tashi Gurung. So, "Are you Mr. Gurung's son?" And he looks at her kind of, curiously and says, "Yep, that's my father. How did you know?" It's like, "Oh, you look just like your father." This conversation is going on not in Tibetan, but in a local dialect that he knew because he grew up in this area. So she invites us into her home and talks about what's going on in this village as far as climate change and having to move from this village. It turns out that her granddaughter, who you see there on the right-hand side, was also there, and she had a different viewpoint, which I thought was quite interesting. So the older woman says, "Oh, look, we've gone through changes before. This is yet another change. We'll make it work. It's not a problem. We have the best foraging ground for the goats and our yaks here. We're not going anywhere. Everything's gonna be fine." The granddaughter, on the other hand, who had several small children, says, "Well, actually, by being able to move closer to the road that's being built closer to the regional provincial capital of Lomantang, they're building a new road through there that's trying to tie into the Chinese Belt and Road Initiative. By being closer to that road, she has better access to food, healthcare, education, and markets so that she can provide a better life for her children." So what's going on in this area in northern Nepal is a combination of a push because of climate change. Yes, it's hard to grow crops up there, and no, it may not be sustainable or even livable anymore, but also a pull because of the road. So it's never quite as simple as we make it out to be, and perhaps as the media makes it out to be. So if we look at this, there's different draws that any of us would want to do to get for a better life for our children. And I should mention the old woman in the picture, she was at the time, I believe, 84 years old, and she'd never been more than 6 kilometers from her home village. So, you know, she's done quite well, and she's lived quite a healthy, long life. That said, you still want to do better for your the next generation. And as modernization comes through, you know there's better options for education, healthcare, goods and services, cell phones, and better foods, and books and entertainment, but also jobs, networks, all these things that people want to come with modernity. So my last point that I want to make is, yep, it's complicated, and it's never quite as simple. And as scientists, we want to make things simple, but certainly now in the time of the Anthropocene, we have to look at some of this complexity. So starting to wrap up, I started off talking about how as geoscientists, our role is pretty simple. We need to understand the physics of these systems. We need to understand the geology, the earth science, the ocean sciences, climate, meteorology. All these things come together and intersect in different ways. To start looking at how to reduce the risk, we need to think about these vulnerable systems, or how these systems can also be resilient if we can do things and put interventions in that can make them healthier. To do that, we need to work carefully with ecologists, with anthropologists, sociologists, economists, and these type of people. Since we eventually want to work towards solutions, we don't just want to sit back and watch these things happen. We also need to work with people like Shekhar, the disaster risk managers, civil and environmental engineers, public policy people, and even investors to think about ways to improve the overall structure of society and the social structures that exist and the physical structures that exist in these exposed places. So the system is very complex, and we need to understand what our role is in these different systems and how to have conversations with other people. And I started off the talk talking about this new word, transdisciplinary. I haven't talked much about that, but in each of these projects that I described, we learn a lot from people who are not actually trained as academics. Now, back in the day, we looked at mostly disciplinary studies. We had our chemists working separate from our geologists, working separate from our economists. More recently, we started working towards multidisciplinary, where you take a university, for example. You have your economics department, you have your geology department, but you're all under the same general ecosystem. As that evolved, we realized also, well, what happens if the economists and the geologists start having conversations? They can find common ground and intersection between their work within this overall ecosystem. And that's where interdisciplinary work started coming through. And those conversations were absolutely critical. Now, I mentioned before also, the real value added in this new paradigm of transdisciplinary is taking that academic interdisciplinary knowledge and busting out of the ivory tower, getting outside of academia and working with practitioners and people, farmers, and guys who are store owners, the people who are actually carving these roads, who haven't been trained in formal engineering. These people know things that we don't. And I think we do very well to learn from them and start thinking about how to incorporate them formally into our studies. So what I propose, and I'd like any ideas to consider, is a manifesto, a transdisciplinary manifesto for disaster research that would go out to our colleagues in geoscience and say, hey, this is a call to action. So in order to create effective and sustainable solutions to reduce the risk by creating true partnerships, real durable partnerships with practitioners, communities, et cetera, promoting a mutually beneficial learning process in order to reduce human suffering. I'm going to end with that. I want to thank you for listening to my talk, and I welcome any questions or comments or ideas for future projects going forward. And I'll go back one slide so you can ponder this one as the questions come through. Thank you for your time, and I will stop sharing if I can figure out how to do that.
Thank you, Brian, for your brilliant talk. Actually, you have one question in the chat box. You can answer that one first.
Very good. The question from Arpan, how big an area can be affected by geohazards like an earthquake? I mean, that is the key question, because we're actually looking at very complex situations that we're navigating here. And in the case of something like the Indian Ocean tsunami, now the earthquake affected a very large area. The earthquake itself caused damage, certainly in Indonesia and the Indian Islands, and the Andaman Islands also. So at least 2 countries, the earthquake itself impacted. But when you look at the tsunami, that is something that was a multinational disaster. It impacted countries all throughout the Indian Ocean basin. And when you think about coordinating efforts of response to these multinational disasters, it was really remarkable to see how the United Nations kicked into gear here. This was one of the biggest disasters that we faced in the 21st century, yeah. And UN had to, at the time, actually change its standard operating procedures. So we were in Aceh watching this happen in real time as they started actually developing this what they call cluster system. So rather than saying UNICEF is going to be over here and they're dealing with children over here, and UNDP is going to be handing out money over here, and environment's going to be looking at the impact of mangroves, they actually started working interdisciplinarily. And they said, look, we can't be in our silos anymore. We have to look at these intersections. So they started forming clusters like education. So for education, they said, for that, development needs to come in here and make sure they have enough money to get through. And we need to have the ecologists come in to talk about the UN environment people to come in and talk about how you can protect ecosystems like coral reefs and mangroves so you will have natural buffers in the future for future disasters. We also have to have UNICEF in here to deal with actual education. So you had 3 agencies that came together under one common cause. That's exactly what we need to be doing. And Shekhar, this is almost exactly what he said we need to be doing. We need to cross over these boundaries and say, what are the problems we need to solve, and who are the people we need to have around the table to solve those problems? It's not going to be just geologists. It's not going to be just engineers. It's not going to be just policymakers. We have to have all of them in the room, and critically to this transdisciplinary model, they need to know their roles, because oftentimes, especially professors, we get cocky. We think, oh yeah, we can fix that. So I can go into a village in Nepal and say, let me teach you about environmental change. Well, they have teachers that can do that better than I can. So why don't I work with the teachers to design a program that works for their particular students, because they know the language better and they know how their students are going to learn better. So the question is, how big of an area is affected by geohazards like an earthquake? You take a tropical cyclone, can go through numerous countries before it loses steam. The monsoon season and the changes we're dealing with that related to the Indian Ocean dipole affects every country in Southeast Asia and South Asia. These disasters are no longer related to countries, they're borderless, and I believe they're becoming, especially with climate change, as they become global disasters, truly global disasters, they can be the size of the planet. And also, as Shekhar mentioned, these fires in California, they're going to have impacts that are going to impact everybody in the world one way or another, be it by long-term climate change or different impacts that I can't even imagine, because I need to talk to somebody who's a fire expert. But thank you for your question. Happy to answer any of the questions also.
Yes, Brian, you have a few compliments, and then one more, this one. Yes, you have a few compliments in the chat box. And I think one more question. No, actually, till this time before introducing you, I was very much envy about your publication. Now I got very much envy about your travel history, seeing all your travel history, especially the Solomon Islands and 5 days trekking to a small hamlet in Nepal. That's wonderful, really. That is the acknowledgement and privilege that a geoscientist get when compared to any other scientist.
Well, the other thing, which I'm happy to be in contact with you again, Sejin, because the work we're doing together is important, but what's more important, I believe, is for you to also do this work and travel around, because the key for getting a lot of these solutions, I can come in from Singapore and offer solutions, or the US, but those solutions aren't going to work as well as the solutions that you and Shekhar and everybody else in this room comes together with to work in Nepal or Pakistan or Bangladesh or even Thailand or Borneo. I think it's absolutely critical that we start considering collaborations between people in the region here in Southeast Asia and learning from each other in this really remarkably diverse ecosystem we have right here. So the more collaborations we can have throughout Southeast Asia and places like the Solomon Islands and Samoa and places that are affected by similar hazards, the better off we'll all be.
And thank you for your wonderful PowerPoint slides. That is very interesting and beautiful to watch, actually.
Thank you.
So thank you very much. I think all the questions are over. Dr. Lindo, you want to say a few words? So Brian, it's from my side and from the organizing field, I am extending my sincere thanks to you, Brian. Lindo, Dr. Lindo, please.
It was really nice to listen to you, Dr. Mccarron. Thank you so much for wonderful presentation. Though I had also a question in my mind, like there is this reduced sedimentation in the coastal area due to the anthropogenic activities that we dam everything in the upstream. So the sedimentation is reduced. So like, as you said, we have these beach ridges that were protecting the coastal community. Because of this change in sedimentation, that may also change the balance in coastal area, right? So what's your opinion about this? Maybe with this, I think Dr. Sajin want me to close this, is it?
No, you can clear that out. We have another 5 more minutes to talk.
Okay, so I wish to have your opinion on this, if you could.
You know, the impacts you're talking about are absolutely critical, especially here in Southeast Asia. So in some ways you have these competing factors, which is really another recipe for disaster. So if you take the Mekong Delta that goes through Southeast Asia, for example, the Mekong River that goes through Southeast Asia and empties out in Vietnam, in the Mekong Delta area, there's tremendous problems with, salinization of croplands. So you have these deltas where they're really beautifully, they've got freshwater source, and they've got lots of nutrients that are coming down the river. However, they're subsiding because I can't remember how many dams. So there's a ludicrous number of dams on the Mekong River right now, which, as you mentioned, is blocking sediment at every stage. So right now the delta is becoming sediment starved, so it's wanting to retreat. On top of sea level increasing is a double whammy, a double problem that's really causing a lot of issues for people in the Mekong River. Similarly, in the Irrawaddy Delta, they're having problems also with salinization also. I'm not sure exactly of all the dams in the Irrawaddy, but it's certainly an issue. Now that's the opposite of what's happening in Haiti, because Haiti's not developed enough to have many big dams and hydroelectric schemes. So what's happening there is the rivers are absolutely choked with sediment. So people who live in the tropics like us, you wouldn't recognize. It looks like something out of Alaska because there's so much sediment in the rivers. It's not something we're used to seeing. So what happened in Haiti, a very interesting example, is all that sediment for the last 300 years has been pushed out to the coastline and really rapid sedimentation out there. So when the earthquake happened in 2010, there's massive landslides and subsidence that happened at the coastline. And some places the coastline lost almost up to 1 kilometer worth of beachfront because it all just slumped into the ocean because of this rapid sedimentation. So there's this constant discussion between how the river systems operate. So the thing we were interested in looking at in Sumatra was if there was a lot of deforestation in the mountains that are feeding Aceh, how that affects sedimentation patterns. We know there's no dams up there. However, because of political unrest, with the Acehnese, when the earthquake happened in 2004, there was actually an insurgency going on where there's a rebel group that's fighting the Indonesian government. So Aceh had been kind of underdeveloped for some time, which is a good thing because it actually helps save their forests. So there's not been much deforestation in northern Aceh, which has been great. So it means the sedimentation patterns are pretty much as natural as they could be, but that is changing. So it's something I want to keep an eye on. So again, how politics come in, history, the history of colonization. There's been massive landscape changes, both during the colonial period, but also during the post-colonial period as economies change and priorities change, as national governments start taking ownership of their own national priorities. So the complexity of the system is just, it's wonderful. It's beautiful for an academic like me to study from it. And it's probably a nightmare for somebody like Shekhar who's got to figure all this out and make sense of it to actually start saving lives.
Thank you so much. It was really a very nice talk. And we also enjoyed nice pictures that you have shown. You started from the coast and take us to the deep India of the Nepal region. It's wonderful. Thank you so much. Since I believe no one else has anything to add with, so we may go to the next session. Isn't it, Dr. Sajin?
Yes, we will go to the next section. Thank you, Brian, for your talk. Yes, we have 1 more minute for the next talk, but during that time, I will introduce the speaker. So next talk will be delivered by Professor Thomas Suman. So he will be delivering on the topic, the role of remote sensing in geohazard mitigation and management. So saying about Thomas, he is my mentor. He is my colleague and moreover a well-wisher. So we got acquainted in 2016 when I have got an opportunity to do my postdoc in Michigan Technological University. So saying about his education and his experience, he took his BTech in civil engineering from Bangalore University, then MS in systems engineering from University of Alaska Fairbanks, PhD in civil and environmental engineering in Tufts University. And from there itself, he took his postdoc also. So immediately after his postdoc, he was appointed as an assistant professor in the Department of Geological and Mining Engineering and Sciences in Michigan Technological University. The immediate appointment itself will vouch for his credentials that he have to get absorbed in that university. After that, he got promoted into associate professor, then now professor, and additionally, he is heading the director of computational and engineering. And saying about his projects, he has a lot of projects starting from the top organization, from NASA, NATO, SCG, NSF, World Bank, whatnot. I do not know what to mention about the projects that he handles. And I hope in the next 50 minutes, he will entertain you all with his experience and his specialization. I welcome you, Dr. Thomas Uman, to deliver your talk. Your mic is mute, Thomas. Okay.
Okay. I hope you can see me and hear me clearly now.
Yes.
Okay, let me see if I can share my screen here. Are you able to see my screen also?
Yes.
Okay. Well, good afternoon, everyone, and thank you, Dr. Sajin, for those kind words of introduction, and thank you for giving me an opportunity to participate in this colloquium that is being organized very well. So thank you for this opportunity. And as Dr. Sajin mentioned, my presentation today is going to be on the role of remote sensing in geohazard mitigation and management. And I would like to walk you through what are some of the remote sensing tools that can be used and what are these advancements that are happening in that area that really would benefit in mitigating and managing or even monitoring, because if we monitor in time, we can actually mitigate some of these things. So that's why refer to it as mitigation and management, how remote sensing can play a major role. So the geotechnical performance monitoring has been a key focus in the community in the last few years. You can see some of the magazines in the US that have highlighted in the recent years the need for geotechnical asset management, which is a term that has come into existence in the last 5 to 10 years. The performance monitoring of geotechnical structures, performance management in practice for geotechnical structures, all of this has been a recent focus in the geotechnical community. Now, why this has come to a high priority? Let me actually explain that to you in the US context from these three maps that I have. On the right on top, the map that you see is the US map with the road networks, which is the primary and the secondary roads. And on that, the red areas marked show the areas identified by the US Geological Survey as highly susceptible to landslides. And now you can actually see in US, several major road networks are highly vulnerable to landslide hazards. So ground movement is actually a huge challenge. Now, if you uh, overlay that same landslide map onto the other two maps, the one on the right and the bottom is the map of the 8,100 major dams in the United States, and the one on the left top is the dams for the levees in U.S. counties, and you can see that both both dams and levees are vulnerable to landslides, and quite a few dams are situated in highly landslide-prone areas. So, if you look at the age of this infrastructure in US, you would see that most of them have actually come to their design life. They are actually already crossing their design life in many cases. So with the aging infrastructure, the uncertainty that we over climate change that we have, increase of extreme rainfall, which I am sure the audience from Kerala is very well aware of. And with all of this, to build infrastructure and to forget is not an option for us. We need to actually have ways to actively monitor their performance. And when I say to build and forget is not an option, it comes to not just dams and levees, but our communities, our houses, our roads, all of this come into place. So I have just highlighted some of the bigger infrastructure, but all of these events, all of these communities need to be actually considered. So we need actually better monitoring systems. Now, traditionally, how do we or why do we use the geotechnical performance monitoring? We use that information to characterize site conditions prior to design, monitor construction activities, performance of the structure for actions during emergency, and floods, maintenance, all of this, we actually use the performance monitoring information. The traditional approach for ground monitoring in terms of landslides and things is to use GPS or inclinometer or tilt meter. Those have been the traditional approach. They are in situ installations which we monitor for ground movement. The traditional approach is quite, if they are very accurate in terms of the data that you can actually get accurate measurement of movements with a very high quality GPS. Continuous monitoring of GPS can give you very precise measurements. You can use tilt meter and inclinometer and some of those instrumentations. That has been the traditional approach. Now, the challenge with the traditional approach is that traditional approach sufficient for the information that we need? How many inclinometers do we need at a site? Is that even practical to be able to install all these inclinometers and tilt meters and GPS? The cost of maintaining and all this installation is very large. So which questions whether is that even a sustainable path for us to take in terms of monitoring geotechnical assets, in monitoring any critical assets. Is that a path we can take? So the answer is it is very challenging with the traditional approach because there is so much cost involved even in the installation, the monitoring, the maintenance, and the number of these installations that we will have to make will be too large to be able to manage meaningfully. So in that case, what we are looking at is how can we utilize some of the advancements that are happening in the remote sensing world for these monitoring as an alternate. And particularly looking at INSAR, LiDAR, and photogrammetry. INSAR stands for Interferometric Synthetic Aperture Radar, LiDAR for light detection and ranging, and photogrammetry, which is an approach using basic photographs that we can actually generate with overlapping images. We can actually generate 3D models. And these approaches can be implemented from different platforms, be it satellite platform, aerial platforms, both manned aircrafts and unmanned aircrafts, and terrestrial platforms where it is either from a stationary location or from mobile platforms where you actually drive along a corridor and try to do the imaging. So we will actually take a look at these three very quickly and see how some of these technologies are being applied to projects. Let me actually begin with a very brief theoretical introduction to the INSAR approach. So the basic idea of INSAR is that you use synthetic aperture radar data. So if you look at the synthetic aperture radar data, it actually measures the two components, the phase and the amplitude. And in that measure, it's a complex number, when, what it measures. And from that complex number, the phase component is the one that is used for ground displacement monitoring. So say a satellite, when it passes through a location, it makes it first acquisition and you have a phase that is being recorded. And from that first acquisition to the second acquisition, there is some change in the ground, some displacement that is happening on the ground. And that displacement can be captured in the second acquisition. And the change in phase can be calculated. So the first thing that you need to actually keep in mind is that between the acquisitions, between that first and the second acquisition, the change in phase can only be, the max change in phase can only be up to half the wavelength of the satellite that you're using. So there are several different satellites. There are X-band satellites, which have 3 centimeter, C-band 6 centimeter, L-band 24 centimeter. So if you are using a C-band data, if the ground is moving more than 3 centimeters between the two acquisitions, then you will not be able to detect that. That will become incoherent. So there is a maximum limit to the displacement that you can actually measure from the INSAR. And in terms of the minimum, you would see that you can actually go very, very accurately to millimeter scale measurements from the INSAR. So here, I just want to show you the equation that we would use is The change in phase is the wavelength divided by 4 pi times the change in phase. So as we are dealing with the wavelengths in the centimeter scale, our accuracy in measuring these displacements are within millimeter to centimeter accuracy, even though the satellites are 800 kilometers away from us. So it's a very powerful technique. And let me actually show you some examples of this technique being applied in ground. So I would like to actually show you a series of case studies here where we have applied this technique to various environments. In this, we will start with an example from in California. Here is the Palos Verdes Peninsula in California, very close to the LA area. And what you're seeing here is the points from the INSAR measurement overlaid on a Google Earth image of that area. And on the legend, you would actually see that the points vary from minus 2.8 standard deviations to greater than 2.8 standard deviation, and each standard deviation is equal to 1.2 millimeters per year. And there is about 600,000 points that we can actually get in this area. So a few things that I want to actually point out. There are areas in this image where you can actually see there is a gap in the INSAR imaging. And that is because those areas, there is low coherence. And that low coherence could be from several factors. It could be because that there is a lot of movement happening there, or it could be from that there is vegetation and there is lack of coherence due to vegetation can also happen. So when there is no point in an area, or when there is lack of coherence that you get, you are not sure what is happening. So there is some areas where you don't know exactly what is happening. In other areas where you see these points are just like an individual inclinometer. So here you can actually see this area, we are actually getting about 600,000 inclinometer data. It's equivalent to 600,000 inclinometer data. So that's the value of such an approach in monitoring, because now you have this incredible amount of information from an area where you can monitor this large area with such a dense points. Now, some areas show red color. Those are areas that are experiencing higher ground settlement. In this case, those are related to some groundwater pumping and areas related to some of the oil extractions in that region. But I will not actually go into that in more detail in this presentation. But I would like to actually point you to an area within that, which is located in the Ventura County, about 100 miles northwest of Los Angeles. And while we were actually doing this large area monitoring, we actually picked this location because this location showed significant deformation happening. And we wondered what is going on there. So this was, we were not actually looking for this area at all. We were doing an analysis of the general area, the peninsula itself. And while we were doing that, we actually found that there was significant deformation occurring in the northwestern part of the Los Angeles. And you can see there are several areas that we picked out after doing that initial screening. And this is one area that I want to actually show to you as an example. So this is an area where there is a dam. The dam is called the Quesatus Dam, which was constructed in 1959, and it is on Lake Quesatus, operated by the U.S. Bureau of Reclamation. Now, some details about the dam itself. Its a crust length is about 2,000 feet or 610 meters. Elevation is about 178 meters. It's an earthen dam. The structural height is about 102 meters, and there was a berm that was constructed. So you can actually see in that image, just next to the crust, there was a large berm that was constructed of height 40 meters, so very large berm. And this berm was constructed between 99 and 2000 due to some concerns that the dam could fail if there was an earthquake loading in this area. And in the LA and the peninsula there is quite vulnerable to landslide, the earthquake hazard. So it was concerning for them. So they actually constructed this berm, which was an addition that was done. So these are some news articles that show that if there was a failure of this earthen dam, it could have significant impact to the community. It could cause human lives. So the retrofitting was done with a budget of about 42 million to stabilize this dam. Now, we actually evaluated this area with the NVSat ASAR data, which is available from the European Space Agency. We used the data specifically from 2005 to 2010. If you look at the NVSat data, you would see that it was available from 2002 to 2012. And specifically, we use the 2005-2010 series, and the spatial resolution of this is about 20 meters, and the wavelength is 5.6 centimeters. So that means we can actually measure up to 2.8 centimeters between each acquisitions. We used a descending orbit of this, and let me actually show you some results of it. So we have some points here. So these are the points that we got on in the dam and in its vicinity. The average velocity were from minus 25 millimeters to plus 25 millimeters. So areas that show minus 25 millimeter are moving away from the satellite. So it is kind of a ground settlement or slumping. Areas that have positive values are kind of uplifting or bulging. So you can actually see some areas we are actually getting positive values. Some areas we are actually getting negative values. So particularly, we looked at a cross section along the crest of the dam. 4 points, 1, 2, 3, and 4, and let's show you a plot of that. So here you can actually see from 2005 all the way up to 2010, and point 4 is the one in yellow, and you can see that that point is pretty stable. There is not a whole lot of movement. There is some variation, so that is within the margin of error. The points 2, which is a light red color, or an orange color, is the one that is having the maximum movement. So within the 5-year monitoring period, it has moved about 45 millimeters And the other 2 points, the blue and the gray ones, have moved around 15 millimeters or 1.5 centimeters. So you can see that the point at 2 is where that maximum movement is happening. Now, we actually did a spatial interpolation of these over time. So you can see a spatial and temporal variation of this. On the left here at the top, you would actually see the date of that image or the interpolation. The first one was from 2005, the month of December. And you can see as I progress through this, that the dates are changing, and you can see how the deformation is happening within that area. So the deformation values are increasing at those locations. At that location where we show that 2, you can see that the deformation is increasing. And also at the berm, at the end of the berm, you can actually see that the deformation is increasing over time. So this is 2008. 2009, and then here finally 2010. So from 2005 to 2010, you can actually see how that displacements have varied within that the berm and the crust. Now, when we look at the crust, what we see is where we identify those deformation, there is actually visible signs of failure happening, which can be detected from the Google Earth imagery. So there is these large failures that we see that are like about 100 meters long of flow that is happening, and cracks that are developing. So there is at that crust, there is actually failure happening that needs to be monitored and needs maintenance. So here you can actually see an instance where you can actually use these remote sensing techniques to identify the ground condition and mitigate the situation before it becomes a large, before it becomes a hazard to the community. Here, in this case, the dam, we inform the dam authorities so that they can actually take action. In the case of the displacement at the berm, we did not see any visible failures there. So this is a case where you can even detect early. In this case, the berm is experiencing more deformation, but we believe it is because the berm is a newer construction. It is actually able to withstand some of that before it is showing outwardly as a failure. So, but this is something that needs attention so that the authorities can maybe even install in situ monitoring devices at some of these critical locations. So the remote sensing can also help you to identify locations where you need to actually put your in situ instrumentation instead of putting it at several locations. You can actually focus and with this instrumentation at some of the critical locations. And in this case, it would be at that location at the crust and the berm where that maximum displacement is occurring. So this is an example where you can actually see the remote sensing being used not only to mitigate a hazard happening, also to guide where the in situ instrumentations have to be placed. When you look at the dam monitoring guidance for existing dams, settlement of the crust or bulging of the slopes might indicate developing problems. That is what the guidance provided by the Federal Energy Regulatory Commission, which is the Division of Dam Safety and Inspection, says. And they actually recommend measurement points should be spaced sufficiently close to allow measurements of all significant deformations. And we can actually see that with INSAR, we can actually satisfy those requirements that the dam safety inspection guidelines that they have provided, and be able to utilize this as a monitoring tool for long-term for dams. Now, let me actually show you another example from a transport corridor. This is from a rail corridor in Nevada. And this is a critical rail corridor that carries a lot of freight from all the way to LA from central part of the US. So any disruption to this route can have significant economic impact. And what we found was that there was a landslide happening very close to the rail line. And with that, the rail company was quite concerned and contacted us to see, to provide them more information on what is happening at this location. And this is actually a brief timeline of that area. And you can see it started, slopes movements began in 2005. Some rotational motions were observed in 2006. Some massive rock slides began in 2011. And from 2011, the rail company has been doing some detailed ground observations. So in this study, we actually used two different satellites. We used the ERS, which is from 1992 to 2000, that was operational. And we used NVSat, which was operational from 2003 to 2010. Now, both the ERS and NVSat had similar sensor configuration, so we could actually combine them and process it together. So technically, we are actually getting almost 18 years of data. But in between, you would see that between 2001 and 2003, we did not have a data. So there is a data gap. So we combine that and process it to see how historically these slopes have performed. And here, let me actually show you some results. So this is, we have the INSAR points from our analysis. And here is the plot, the time plot of the 3 points that we got from the slope. And what we can see is that point was very stable until 2005. So from 1992 to 2005, that period, almost 13 years, there was no movement happening at that slope. And then all of a sudden, that slope started moving. And you can actually see as time progressed, there was about 62.4 or around 62 to 66 millimeters of movement on that slope when some of that failures started happening. So that is probably the warning time. That way, time could vary from site to site depending on the conditions, but you can actually see here, in this case, after about 62 millimeters, the site started experiencing some physical failures. Now, our question was, why did it all of a sudden start moving in 2005? Was there a tectonic activity there? What really caused this failure to, or the slope to move in 2005? So what we found in our forensic investigation is that there was a major flood event in that area on January 12th, 2005. You have actually some photographs that are time-stamped, and which led to derailment, and several rail cars got derailed in this area. And being a critical route, they actually put that route back very fast. They needed the route to be reestablished so that the trains could move. The needed resource for transportation, and for that, what they did was they actually blasted some of the slopes along this corridor, and that led to destabilizing some of the slopes. So they used that blasted material to put the track back. So they got the track back very fast, but that created more problems for the rail company in the long run. And it is actually becoming a challenge with several locations along this corridor being destabilized due to this blasting. So here you can actually see the application of remote sensing for forensic investigation. You can actually look back. In this case, we were able to take a data set all the way from 1992 to 2010, which is not possible when you're doing some of this ground monitoring where you actually have one or two data points that have been placed just when the infrastructure was there. You cannot actually look historic performance of that area, and that's one of the main benefits of remote sensing. Now, after we identified the problem for that, the rail company asked us whether we can actually proactively identify other locations along this corridor that needs to be stabilized, and we actually did that. And here you can actually see some of the areas that we found as unstable, where we did field visits. This is an area that we found to be stable, so this was not within that unstable area. Another example of a stable area. And here you can see an example where we identified as unstable, and the rail company went ahead and stabilized it by shotcreting that site to prevent a failure, especially there was not a whole lot of catchment area there from the failing slope to the rail line. So they immediately went and did stabilization. So this is an example where you can actually see the remote sensing approach can be used as a proactive method to not only identify the sites that are that have failed, but also to proactively predict where the failures will be and mitigate them beforehand, before it becomes a hazard. So let me actually give an some of you may be aware of this, that the NASA and the ISRO are planning for a SAR mission together. Right now it is planned for 2022. It is actually moving forward. It's in the very final phases of the launch. It is going to be an S and an L band SAR mission with full global coverage. And this is going to be a very exciting launch for the geoscience community, for geoengineering community, because this is going to provide us global coverage and data set to monitor some of our critical assets and ground hazards. So this is something, if you are interested in this work, you might want to actually follow the launch of this satellite. This is actually going to provide us a very valuable data set. For a long time, for a few decades now, US and the NASA and the US SAR community has not had a SAR mission. So this is exciting that the NASA is joining with Indian Space Research Organization for this joint mission, which is going to be called the NISAR mission. Let me also show you some examples of what we can do from photogrammetry here. In this case, we are using a DSLR camera, which is nothing too fancy. It's a Nikon D800 camera. So you can actually use this technology with most DSLR cameras that have a fixed lens. Um, and we process this using Agisoft Photoscan. There are also other open source processing softwares that are available. In this case, we did that at that same site in Nevada where that ground failures were occurring that we measured using the SAR. And when we do this photogrammetry, one thing that we need to keep in mind is that very precise ground control points are needed if you need to develop accurate displacement maps. So in this case, you can see our ground targets. We had a ground target and we placed GPS, we acquired GPS data with very high precision at these locations. And that is critical in term for your 3D model development. And you can see in this image, we have several targets that are placed that we could utilize to be able to stitch all those images together. So this whole approach of photogrammetry is called the structure from motion. This has been an area that has been significantly advanced by the computer science people, especially for virtual reality and gaming and all of that. But there is an area within that the geoscience community can benefit from, where we can actually generate 3D models over time and monitor locations. So here, let me actually show you a video that compares the photogrammetry points that we generate to a LiDAR. Now, if you look at the cost comparison, the LiDAR, a reasonably good LiDAR instrument would cost you about 50,000 US dollars, whereas a photogrammetry from a UAV these days is less than $2,000 investment. So there is a significant difference in the cost of those initial cost. And you can see a comparison of these two data sets. The larger scene is from the LiDAR. The smaller scene within that is from the photogrammetry. I will actually turn off one of those scenes so that you can then focus on one. But this is a comparison between the two. You can actually see both are merging almost at the same location, so very accurate. You can get information on the track. You can even see some of the power lines there. You can see the failure happening there at that the landslide location. And this right now, what you're looking at is just the photogrammetry. So the LiDAR is turned off. This is just the photogrammetry. And you can see a very, you can see the head of that landslide head scarp. You can make very precise measurements. And here, in this case, you're seeing just the LiDAR. So both the LiDAR and the photogrammetry are giving comparable measurements. In fact, the LiDAR is suffering from some shadow regions. The LiDAR has the LiDAR had shadow problems because this was a terrestrial operation for LiDAR, whereas in the case of photogrammetry, we used an aerial platform. The aerial LiDAR are much more costly than what I said about the terrestrial, which is about 50,000. So the aerial LiDARs can go up to around 200,000 US dollars. So compared to the cost of the LiDAR, the photogrammetry is much more cost efficient operation to get 3D information of an area. Now, we use that same operation in Alaska to monitor a landslide, which I want to actually show to you quickly. It is near the Yukon Bridge in Alaska. You can see on the bridge, there is this pipeline going, which is the pipeline that carries oil from the north slope of Alaska to the Prudhoe Bay, from the Prudhoe Bay to the Valdez. So you can, this is a critical infrastructure. Any disruption to this pipeline can have huge economic impact. So they were actually concerned about the landslide that is forming very next to this bridge, and they wanted us to monitor this, and we did the monitoring, and you can see the detail that you can actually get from this photogrammetry image. So this is a 3D point cloud that you're seeing. So very precise measurements you can actually make within that landslide. Now, the first point cloud was generated from 2014, and the second point cloud the very next year. You can see some of the changes happening there. There was a drilling group that was doing a drilling to understand the soil characteristics, so we can, and from these 2-point clouds, we did a change detection. And we found was there were some movements happening, but these were very minimal compared to, and there was no systemic movement happening. It was more erosional. So there was some material being eroded from within the landslide and getting deposited at the base of the landslide. So some of these blue areas are where the depositions are happening. The red areas are where the erosion is happening. So it was more erosional features that were happening there. There were no major failures forming at that location. So we can actually identify these conditions from the photogrammetry. Similar approach we have done to monitor pipelines. In this case, you can actually see in this video, you can there is a pipeline corridor where we did this work over time, and we can actually identify the slope failing. In this case, you can see that the ground is, the arrows are going down here, which indicate that the ground is going down. So there is the slumping occurring here, and at the toe of the slope, you can actually see that the ground is bulging up. So there is a classic rotational failure happening here. The ground settling at the head of the slope, and the ground bulging at the toe of the slope. So this is the kind of work that you can actually do from the photogrammetry to be able to identify conditions before it becomes a failure or a hazard. So some of the summary that I want to leave with, in the case of INSAR, you have a rich data archive for forensic investigation. You can actually do millimeter scale movements from satellite platform using stacking techniques. And the INSAR provides an opportunity to proactively monitor infrastructure with improved spatial and temporal resolution. So this is a very exciting opportunity to be able to use INSAR for monitoring ground movements. The photogrammetry, user has more control on the temporal resolution. You can actually decide when to go out and collect the data. It is cost effective compared to some of the other techniques that we have, including LiDAR, and it provides centimeter scale accuracy to monitor ground movements. Very simple processing, and it is an attractive approach for many infrastructure monitoring applications. So with that, I would like to actually thank the funding agencies and some of my postdocs and graduate students who have worked on this project, and the funding agencies who have made it possible to do some of this work. So with that, I would happy to take any questions, and thanks to the organizers for
Thomas,
giving me this opportunity.
2 questions and a few compliments are there. If you can answer the 2 questions in a very quick moment, because it's time for the next talk.
Okay. So am I able to, let me, okay. So I believe the question is how to differentiate between anthropogenic dislocation and natural landslides. Well, you will have to actually understand the area to be able to identify whether it is anthropogenic or natural. From the remote sensing, what you would actually get is more the ground deformation. So you will have to dig more into other details to be able to identify that. In terms of INSAR data available for free, yes, the Sentinel satellite from Europe has very good data for INSAR work, and it is currently available for free. Also, once the NISAR mission comes, that data set would be available for free. But right now, if you want to use, there is Sentinel data available. Also, there are historic data sets that are available. And in fact, many of those data sets are available for free for educational institutions. In our case, all the examples that we presented were using free data sets.
Yes, I think the questions are over. Thank you very much, Professor Thomas Suman, for waking you up early in the morning, in a cold morning. I know there you were under blankets. So thank you very much. And actually, Thomas was insisting me from 2016 onwards to give a project on monitoring the dams in Kerala as well as the Konkan Railway. But I was a little hesitant to apply because the Indian Railway itself will not take that such type of projects, and even KSEB I do not know. So instead of knocking the door without any result, I didn't apply it. But I think someone who is listening to this can apply or can collaborate because with this one, University of Kerala also have started using INSAR awards and processing, etc. And we have come up with the 2 publications. So with the time limit, sorry, Thomas, I was not able to ask the other participant to ask any questions to you. Thank you very much for your wonderful talk.
Thank you.
And next is Professor Kees Van Westen. I think there is no need of introducing Van Westen to any of the participants here. He is one of the highly cited landslide experts in the world. Not only he, I can say that rather than you can understand the importance of his thing by knowing his disciples. The first speaker who have done the keynote address is a PhD student, that is Shegar Lucas Kuriakos, is a PhD student of CASE. And tomorrow's speaker, Dr. Thomas Martha from NRC, he is a disciple of CASE Van Westen. Then another is Dr. Saibal Ghosh, who was heading the what is an IGC, International Geological Congress, which was now postponed, which was expected to be held in New Delhi. And Pankaj Jaiswal, who is leading the landslide division in Geological Survey of India, a lot of disciples. So I'm not saying anything more about Van Westen. And actually, I also got acquainted with the Van Western after the 2018 flood, where we also have worked together for creating the landslide inventory of Kerala. And everyone will wonder that about 4,426 landslides we were able to map for the 2018 anomalous rainfall alone. And say I cannot say what is in the number of publication here have. I think better I will not say more about Van Western because everyone knows you, and because of time limit, I request Professor Case Van Western to start your talk. Please, Case.
Thank you very much, Sajin Kumar, for your very kind words. Let me share my screen. Okay, I hope you're seeing my screen now. Probably you do.
Yes, we are able to see you.
Okay, so sorry. Yeah, thank you very much for this invitation. I'm very honored to be in this in your conference. I have also listened to some of the previous speakers, and it's really interesting to hear this in such a condensed form. I'm going to talk a bit a different topic. I'm looking at what do we do with the information on hazards. In fact, between the talk of Shekhar and the talk of Professor Oomen, really looking at how we can express the losses of hazards, and also how we could use that in decision making. Before I do that, let me explain you a little bit about my organization. It's a bit different from a normal university. We are originally in international postgraduate training institute, focusing from people from developing countries. We were founded in 1950 by the first Dutch prime minister after Second World War, who was a geodetic engineer and who wanted to do good for the world. So he established this training institute, and it dealt with map making. And over the years, it's developed, of course, also with the technology developments, remote sensing, GIS, web GIS, all different approaches are being incorporated. Our major focus still is capacity building and training. We have more than 20,000 alumni. And well, as Sajin Kumar mentioned, a lot of them, most of them go back to their own countries, and they play an important role in the earth science and disaster management field within their country. Of course, ITC is wider than disaster management. It deals with geoinformation and a lot of different application fields, ranging from urban to agriculture to water to mineral exploration, but also in the field of natural hazards. So we focus on capacity building, even though we've become part of a University of Twente, which is the local university in our city. We are also putting more focus these days on PhD research, jointly with organizations in the south. Through that also we collaborated, for example, with the Geological Survey and with NRSC. And we are now also collaborating with KSDMA and with University of Kerala. So, of course, would have been much better to meet you in person. I have visited your organization of the Kerala several times, but last time a bit more than a year ago. Unfortunately, that's no longer possible. But on the other hand, given the number of conferences and talks that I have been involved with in the last month, it would never have been possible to do this physically. And so as it's also much better for the climate that we do it in this way. But still, I think it's important to visit Unfortunately, due to the spread of COVID virus, we are not able to do that. I see India severely hit, but actually getting out of the wave, as it's visible on the lower right side of this graph. And unfortunately, the Netherlands is kind of starting a second wave now. We are, as you could see, since 1.5 months about in a second wave of the virus, and so we are kind of second lockdown. Although there are hopeful signs that we are now already over the main top. So in this talk, I would like to discuss about, say, keywords changing multi-hazard risk for disaster risk reduction. And the aim is how we could model different hazardous processes in the same area, how they change over time, and how they would affect risk, so the impact that they would cause, and how we could use that changing information in decision making, where we would focus also on areas with limited data availability, and also more looking at, well, different scales, but also mainly also at local levels. So when we're looking at the individual components of those, we are looking at the changing component. And so these changes could be slow, well, relatively slow when we're thinking about climate change and its effect, which would produce maybe an increase in frequency of certain types of hazards, but also the appearance of hazards that had not been very prominent in certain areas before. So it also means we would have a change in hazard types. And we would also look at changes in land use related partly as a feedback to climate change, but also to economic, political, demographic developments. Of course, these have a link, and our research as such is not so much to model those changes, but to use those changes in how they would affect the hazard and how through changes in hazards and exposure, it would change the risk. And then see how this could be used to make better judgments about how to reduce the risk. These changes could also be very fast, and those would be changes specifically that occur after major disasters happen. So major disaster events like huge earthquakes, wildfires, volcanic eruptions, but also tropical storms, they would change the landscape conditions, changing also the aptitude of the landscape for future hazardous events in a significant manner. And very often the landscape needs to have a certain time to bounce back, so to reestablish a certain equilibrium. We've seen that, for example, in areas like China, in Sichuan, after the major earthquake that happened 2008, where still, I mean, more than 10 years after the earthquake, huge debris flows are happening, which are much more frequent than they were before. So these changes can also be planned. So they can be planned changes, so mitigation, risk mitigation measures. Shekhar said also in Kerala, there's also a policy to persuade people to move to less dangerous areas. And so that these could also be worked out as, say, kind of scenarios, alternatives that could be evaluated, and also in the recovery planning. So build back better is an important term. And after a disaster, it's also important to develop different recovery scenarios and also see what would be the risk related to these recovery scenarios. The second level here is what we're looking at is multi-hazards. So they could be related to specific triggers, but they have also an interrelation with each other, and those would have an important effect also on the risk that we do. Then we're looking at the risk itself. So the components of the risk, so the exposure, the vulnerability, the capacity part, which risk methods could be employed, which risk metrics, are we using population risk, monetary risk, and for which kind of intervention or decisions do we use that information, and also what would be the scale at which we do that. And eventually we do this for disaster risk reduction. So we develop risk analysis for specific applications in, for example, early warning, for example, impact-based forecasting. So the early warning not of the event itself, but of the damage that an event might cause, but also through mitigation planning and development of spatial decision support tools for that. So that, in a nutshell, refers to, say, the aspects that we would be looking at. We start with the part on the multi-hazard part, so multi-hazard interactions. The interaction between hazards will have also a large effect on how you would estimate eventually the risk associated to that. So hazards could be completely independent, occurring with its own magnitude frequency relationship, but affecting the same area. And in that case, they could be evaluated separately also in terms of their hazards and risks. Take earthquakes or flooding, for example, that have a completely different trigger. They could be compounding. That means that one hazard that's independent of another, but occurring in the same area close after another event, will cause much more impact than if it would not occur close to each other. So we see that also with the effects of natural disasters happening now in COVID period, where there's much more difficult to provide rescue operations because of all kind of restrictions related to COVID, as we see in some countries. They could be coupled events, and there's quite a lot of events that are coupled. That means they share the same trigger, but they might affect the same area. For example, during a tropical storm, you could get a flash flood, you get a storm surge, high winds, landslides, and they would all affect the same area. And so they are interacting. So you would need to also look at their damage that they cause in a combined manner. Then we have the kind of what most people think as multi-hazard is a domino or cascading effects. That means that one hazard actually triggers the next, etc. Typical examples of those are earthquakes triggering landslides, landslides blocking rivers, causing flooding. And so overall, in some areas, earthquakes and floods are not independent events, because floods might be caused by earthquakes if they happen in mountainous areas, blocking river valleys. So that it just shows that it is a really complicated issue. Also conditional, that means that hazards change the conditions in the terrain, making it more suitable, vulnerable to other events. So these multi-hazard interactions make a very important a challenge in the whole study. So when we're looking at risk, we have a number of different components, and these we call the risk components, and these have all their own special aspects. The risk at the end is the frequency, the probability of losses of a certain type. And you could see that simple as the multiplication of hazard frequency multiplied by the consequences. The consequences would be the amount of exposed elements at risk and their vulnerability. So in we looking at the individual components, hazards have a important three components: the frequency, the spatial extent, and the intensity. And so these would be the ones that we need to model, but also depending on these hazard interactions, need to model them in combination with each other. The second component of the risk are the elements at risk. So all, say, everything that could be in principle damaged by hazardous events. Of course, we can't quantify all of that. So in many applications, we would limit ourselves to the main types of elements at risk that are most important for a specific study. And that again depends on the aim of the study that you do for your risk assessment, whether it's a study for, pipeline infrastructure, as was just shown in the last example, or for schools if you work for a Ministry of Education, or it's more on a planning level where you're looking at different land use types, could be agricultural level. So these would be determined what type of elements at risk we're looking at, and also how do we quantify those. So that is an important aspect. The interaction between those two, hazard footprints and elements at risk, we define as exposure, and we analyze those using spatial tools like GIS. And we also bring them together with what we call vulnerability, which is the conditions that cause damage. And so you could think of those as physical vulnerability. So the objects that might have damage due to the that they're being exposed to a certain intensity of a hazard, a certain water depth, a certain earthquake acceleration, and these will behave in a different manner. So we try to capture those through vulnerability curves or fragility curves, or we try to do that also in a more holistic manner, where we're looking at the different different dimensions of vulnerability, including economic, social, environmental vulnerability. And very often we do that using some kind of indicator-based approach. A good example of that is the risk-informed method developed by the Joint Research Center in Europe. So if we look overall to the risk assessment methodology, we would look at the data inputs. We look at the susceptibility and the hazard part in yellow. In blue, we look at exposure and vulnerability assessment. And the red part, we're looking at we combine that information into the risk assessment, where we look at specific risk scenarios first in a loss calculation. We integrate those in the risk assessment. So when we do that, we need a lot of information that would have to be available. And it's also one of the limitations that it requires information on all these three risk components, and also how these change over time. So there's a lot of high demand for spatial data. What I have seen myself over the last 10 years, an enormous say growth and availability of spatial data also in countries like India. Whereas this is a picture of the persons that Sajin Kumar was talking about, including Shekhar. When we did the work 10 years ago, we had to struggle to find DEMs and all the other things. Whereas nowadays, a lot of information is available on national platforms like Bufan from NRSC or Bhukosh from the Geological Survey of India. So in that sense, a lot of developments have taken place, including, for example, here, say inventories that have been made for specific events. But in reality, we are still a lot of short of spatial data, although enormous developments have taken place. I would say really a lot of developments are now there in terms of data availability at the global level. Historical disaster databases are very now much more becoming available, not only through EMDOT, but also at the local level through, say, initiatives like Desinventar. Remote sensing specifically has been taking enormous leap. And so a lot of data sets are now available globally, also at a fairly large resolution. And also in terms of digital elevation data and thematic data, take, for example, geology or land cover or soils, relatively good data becomes available globally. Good example of that is, for example, soil grids, which provides, say, soil information on in terms of granulometry, soil thickness, based on many soil profiles using a geostatistical approach for the whole world. Also at the level of elements at risk, a lot of developments took place. So when we're looking at elements at risk, we have to decide whether we deal with that in which spatial form, as points in critical facilities, for example, linear elements when we are dealing with transportation infrastructure or lifelines, building footprints, which is often used at the local level, or land parcels or land use based assessment when we also want to project it into the future, or in grids, which is done very often at the more regional or global levels. How do we get such type of information? We could use existing databases if we are lucky. The Netherlands, for example, I could just go to the website indicated here, find the information on my own house. Many countries don't have that, so we use existing data sources that are providing a piece of that puzzle, so like built-up area databases. We are now developing a lot of, for large parts of the world, this data through collaborative mapping, using OpenStreetMaps, OpenStreetView, Mapillary. But in a lot of cases, the data which still has to be collected within a project setting, unfortunately. And there are, of course, also a lot of developments there in image classification, now also cloud-based, using Google Earth Engine, for example. But still there are major problems with respect to the scale, to the completeness of the data, so whether such data is available for the right moment. Take, for example, OpenStreetMap data is often not updated, and so it might represent an old situation. The spatial aspect could be a problem because it represents grids that are too coarse. And most difficult is the attribute information, whereas we do have good information on where built-up areas are, but we lack information on a good description that we need for risk assessment, such as occupancy type, value, and people. So there's a wealth of information also available now from remote sensing-based data sets. Here, just a list of data sets available for land use land cover, which are at good resolutions, 100-meter resolution globally for different years now with Copernicus data. Korean land cover data is already available since 1990, so also over time you could do that. And when we're looking at gridded population data, we also see major developments where DLR, the German space agency, has already developed global human settlement layers with 12.5-meter resolution. So these are really becoming very detailed, but they're not yet at the footprint level. So normally what they do is map the urban areas, project the census data on them. So when you use these data sets locally, they would have a lot of issues because the land cover information is not properly incorporated in them. So when we then look at the hazard characteristics, we need to collect information on, say, the type of hazards and also their hazard interactions. We need to spatially represent them at the right manner. And we have to have an information on the frequency intensity of these events. And that these two are perhaps the most difficult ones to assess. The frequency often is done either by collecting historical data on the events themselves, as in the case, for example, of earthquakes or stream gauging stations, or indirectly by the triggering event as such. For example, in the case of landslides, where we actually link it to rainfall or to earthquakes. So we depend very much on disaster databases, which are actually quite different from hazard databases. We actually would like to use hazard databases, but these are much less developed than what we would say disaster databases. The disaster database contains information on the disaster itself and its consequences. So number of people affected, number of people killed, economic losses, whereas a hazard database contains, if it's correct, the mapped event with information on what it actually was. So the spatial components very important, and the date information. So location of these information is often lacking. And so using disaster databases as a start point for such analysis often creates problems. And so one of the key aspects is also to further collect these hazard databases. So there's a lot of different methods for that that are listed here, where we could use archives or field methods or any other methods indicated there. But we always have these issues of completeness and accuracy in time, in space, and with respect to the information itself. And that is an endeavor which requires a long-term effort of collecting such information over longer periods of time, so that we are better able to make that link between intensity and occurrence. So as also was shown in the previous example, our new tools are really very helpful, such as multi-temporal DEMs, also for mapping landslide occurrences. I think we've just seen that, but also new tools on machine learning methods for landslide detection. Here an example from Nepal that mapped the landslides that were caused by the earthquake in 2015 by one of our collaborators using different machine learning techniques. But also these automated methods still may have certain issues. We came across that in a study we did in Kerala after the 2018 monsoon. Sajin Kumar and Rajanis from University of Kerala were also involved in there, and Brian as well as Tapas Marta from NRSC and Pankaj Jaiswal from GSI. So we wanted to know eventually, also together with UNEP, UN Environment, what was the relationship between those landslides and land use change. And so in order to know that, we need to first we have a proper mapping of where the landslides happened and also where they initiated, so that we could see the areas where they initiated, what was the land use change in those specific areas. So we did this actually initially using available inventories, and these were one inventory generated after the event by NRSC as an emergency effort, so to help the recovery. So based on resource data, it was using an automated mapping approach. And another data set we obtained was from GSI, where they sent teams of geologists to the field, visiting the areas that actually had damage reported. So most of them were buildings destroyed or roads destroyed. And we combined these two different types of data. So it was about the, the major event in 2018. Most of you probably aware of that. It's a huge amount of rainfall fell within a relatively short period of time, causing very large flooding and landslides. And so we we were integrating these two landslide inventories by visually interpreting these on Google Earth images. Why Google Earth images? Because Kerala is very large. If we had to use very high resolution satellite images, it would be extremely expensive to get them, and also for different periods. So what we did was we used them in Google Earth. We mapped what was the exact location of the landslide, what was the land use at that moment, and what was the land use say 8 years ago. That was a kind of period for which we still had good coverage of high resolution images. So we came across a lot of different issues there that say you have to adjust the automatically derived landslides made from satellite images because they were mapping also some other areas, or they had some omission errors and so on. And so eventually from these data sets, we we had an original data of 1,400 landslides from GSI, from the mapped landslides in the field, and over 5,000 polygons in NRSC database. And after, say, the checking and also mapping new landslides that were not in there, we created a final inventory of about 3,700 landslides. So based on their types and also their the source, we would be able to do the analysis for the whole of Kerala, and specifically also for the most affected area in Idukki, where we then analyzed what was the land use land cover change in those landslide locations, and also checked if then these changes in land use land cover were very different from the ones overall in the area or in the landslide susceptible areas. So this is a study that we just completed now. Is also being published. The next aspect within the hazard, the risk assessment approach is the hazard modeling. And when we're talking about hazard modeling, we're looking at multi-hazard modeling. And there are actually relatively few of these hazard chains that have been formally developed into hazard models. Here's one example, which has been generally the best modeled, is the tropical storms and its individual effects related to rainfall, storm surges, and wind speeds. So there are also calculation tools that allow to do that. Other examples for flooding, where they have been able to do this also for current period and future scenarios. So when we're looking at more local level hazards and the hazard interactions, we we have much more problems in doing that. As you could see on the right side, a whole multitude of different models have been developed to try to capture these interactions between hazardous processes at the local level. However, often they are only one pair of events, not multi-hazard integrated ones. So we developed also one of such models. It's called OpenLISEM, which tries to model all the hydrometeorological effects of an extreme rainfall event caused during, for example, a tropical storm, being it both a landslide initiation, rainfall runoff, the mix between the water coming from rainfall runoff with the sediments delivered by landslides producing debris flows, but also landslides that could be damming river valleys. So of course, such kind of models are generally rather data intensive, although we tested them out also in areas which are much less data intensive. Here, one example of such a study. We did this in well, different parts of the world, but also in the Caribbean, where we worked on several islands, but the island of Dominica is one of the islands that was very heavily damaged by a tropical cyclone, causing a lot of damage in terms of flooding, wind damage, storm surges, landslides as well. It's a small country, and it was affected already in 2015 by a previous storm. So we did also this for the World Bank in the project, and we developed a web-based portal to support with respect to hazard and risk management. So for this particular event, this was a real major event. We mapped the landslides that occurred within the country. Thousands of landslides happened, but also merging together in debris flows. So you see all the red areas here were affected either by landslides or debris flows during that same event. We did this mapping for UNITAR UNOSAT using Quesatus images that we obtained. And these are two examples of the output of one part of the country with the types and also the components of the landslides. For the same area, we had mapped from previous events landslides in different years. So here, 1987, 1990, 2014, 2015, and now 2017. So mapping events over a long period of time, linking that with that trigger, allowed us to make much better predictions on, say, the probability of occurrence with relation to a specific time period. We also simulated those events using these physically based models. To the right side, you see the results where the red are the landslides modeled and the green are the ones mapped. To the left, you see the image before, and this is the image after the event. You would also see that there's a marked difference in the quality of the data. To the right, we had only general digital elevation data, and here we had LiDAR data, which improved the results a lot. We were also able to simulate failure depth, so how deep the landslides would have been, and then also how the flow would happen. So the flow of events during this event. Here you see the simulation of the event itself with the landslides happening during the event, and in blue, the flooding happening. And say the multi-phase flow, that means the water and the sediments were modeled and represented here as a matrix between percentage of solids and the flow height of the material. We also used that for calculating the peak discharge, and those points in the map here are all the bridges on the island, with many bridges were actually washed out during that event. And World Bank is also interested to develop a bridge risk index where they need such type of information on peak discharges for such areas. Debris volumes, another aspect. So how much material is actually deposited after such an event. So if they are not dredged, the next event would cause even more severe flooding because the whole valleys are filled up. And so this kind of modeling also allows to model debris volumes. Here also a more detailed example of that, where you see drone images before and after with the elevation difference mapping the depth of the materials, and on the right side how we mapped the modeling part. So eventually we would like to have information like this, so multi-hazard maps that would represent different types of hazards with different intensities and for different return periods. Now, this would allow us to do a real proper risk calculation. And then we would be able to do that for the current situation, for future scenarios, and also for specific planning alternatives. When we do such risk assessments, we can use a multitude of different tools for that. They could be quantitative, they could be semi-quantitative, or they could be purely qualitative. There are a number of tools available, but each of those have their specific limitations or only focusing on one specific area. So in practice, there's a lot of times we actually have to develop our own calculation tools. Here, one example of those, of a study we recently completed in a national scale study in Tajikistan, where we calculated multi-hazard risk for 7 types of hazards combined with 4 types of elements at risk. And so we were able to, we developed a platform in which users can visualize, okay, the hazards, the elements at risk, the exposure, the losses, and the average annual losses at the end. So that requires also a development of such intensity frequency maps. And for some hazards, we didn't have enough information on frequency and intensity, so we were using susceptibility instead. Part of that was also development of elements at risk using built-up area, and also classifying those built-up areas using crowdsourcing mapping. We applied vulnerability analysis, but at the end, the aim was to, we developed a tool where you could select any administrative area and then make any combination of hazards and elements at risk and generate a report specifically for that administrative unit. So a specific information on the risk within any administrative unit within the country. The last example I want to show you is an example of changing multi-hazard risk for decision-making at the lower scale, a study that we did in an urban area in Colombia, which has a very rapid growth, a city of part of the city of Medellin, where we looked first at modeling the present hazard, the future changes, both urban growth and climate change, and also looked at possible planning alternatives. So we would see which alternatives would be best if we, under different possible future scenarios, all based on the risk calculation. So it's done in the city of Medellin, as I said, on one part of that called Envigado, located on an alluvial fan, which could be hit by flooding and debris flows. So we applied this type of modeling for different return periods and obtained a series of intensity maps, which we then combined with element at risk classification and with physical vulnerability curves to calculate the average annual losses for the current situation. Then we introduced several possible future scenarios, in this case related to climate change in terms of the frequency change in those extreme events, as well as population change and its effect on land use. So population change was based on a growth rate per year of population and also on the requirement of new buildings that were planned within certain areas. And climate change was based on the higher frequency of events. So this would produce then many hazard maps, as we did this type of study then for a future year, like 2050. Also different elements at risk maps and also new vulnerability information. So we calculated then the risk now, but also the risk in future, how that would change in 2050 based on population scenario and on the combination of population and climate change. Also visually, that could be shown where you see certain areas within the city having a large increase in risk over time. So these would be prioritized for risk reduction. And then the last step was to analyze what would be the risk reduction alternatives. So what could be done to reduce the risk? And given these scenarios, which risk reduction alternatives in terms of addressing vulnerability or addressing physical infrastructure would be the best. So different alternatives were evaluated, such as channel interventions or sediment retention basins or flood-proofing of underground parking garages. And based on that, the combination of these with the climate scenarios, of the future scenarios, allowed us to see, okay, how much the risk would be growing if we don't have any measures and how much it would be growing or reducing when we implemented the measures. So these calculations of risk would allow us then also to use cost-benefit analysis to see which of these alternatives would be the best. We're currently developing this into a spatial decision support system where that would be web-based and where users can upload their own hazard elements at risk and vulnerability data and do these type of evaluations for possible future scenarios and alternatives. This was a rather rapid glance through how changing risk could be analyzed. For those of you that would look for more, we are an international training institute, so you're most happy to visit us, perhaps for a short duration training, perhaps for a master course, or even maybe as a joint PhD. I thank very much all the collaborators with whom I collaborated, also from India within several of the things that I showed. So thank you very much for your attention.
Thank you very much, Case, for your wonderful presentation. And I'm sure that everyone was excited or happy to hear your talk. And I think there are a few compliments other than there is no question. Yes, one question is there in the chat box. I want to read it for you, or you can do it.
Just trying to find out where
the last one. Which are the anthropogenic activities mostly influence the landslides in Kerala? What is your suggestion on management?
Oh, okay, definitely. Yeah, so which anthropogenic activities most influence the landslides in Kerala? Interestingly enough, of our study, a very large percentage of the landslides we found during the 2018 event happened in forest areas. But then the actual anthropogenic activities that were mostly affecting it were related to cutting of slopes in relation to either, mostly to buildings. I think that was definitely one of the major causes of landslides that we saw in relation to land use change with respect to anthropogenic activities. But it was also striking to see how many of those landslides that we saw were triggered in forest areas. That was more than we had expected, honestly.
Yes, I think to wind up before that, I request Shager is there. Actually, I think Shager, you can say a few things. Your experience with the case or anything else, whatever you want. I think
my experience with Case, thank you, Sajjan, for this opportunity. My experience with him is why I am here. But
Hi,
for him, I
Shekhar.
wouldn't have been here. Hi, Case.
Hello. Good to see you.
Yes. It is quite interesting to again listen to you, Case. I was sitting here through all these presentations because although I was doing a lot of other things in the background, I was listening to all three of them. I'm very passionate to hear Brian and Thomas and Case. Well, for the young generation here, if you are looking at a mentor, then you have Case here. I am, as Sajjan was telling, a testimony to what he would take a raw material like me and transform into. So, well, ITC is such a big family, as you know, and we are very proud to be ITCians always. And if you were looking for a professor who is most cherished in ITC, then you have Case here. So thank you, Case, for having talking to all of us again and enlightening us. And Thomas, at that point of time, I didn't want to interrupt because Sajjan was telling that he had limitations of time. But it was very excellent. I requested you for a little document that you would be able to send, I hope. Brian, once again, thank you for teaming up with Sajjan and enlightening a lot of young minds here. So from SDMA side, we will continue this collaboration. Sajjan is formally part of SDMA's advisory committee now. So there are a lot of things that we are trying to do together. And yeah, thank you, everyone. Thank you for this opportunity. And thanks, Case, for coming again.
Yeah,
Thomas,
hopefully at some point in time we'll see each other.
Yeah. Once again, I had a chat with the Deputy Consul 2 days back under the Netherlands Kerala initiative, and he was telling that I could still travel if I wanted. So,
Okay.
so they are giving a window, it seems. So
Okay.
we'll hear.
Yeah.
We'll hear from him soon, and then I'll communicate to you.
Yeah. Well, let's first also wait until the university opens, because going to a place which is closed, this makes no sense.
Exactly. Okay, guys.
I think Thomas wanted to say things. Yes, Thomas?
No, I just wanted to echo the same here. Great presentations, Case and Brian, and thank you to the organizers for this opportunity, and thanks to Shekhar for those work that he's doing at KSDMA and the opportunities to collaborate with KSDMA. And Shekhar, yes, I'll send those documents to you. Thank you.
And Case, there is a message for you from Rajanish. Actually, Rajanish is very happy mentioning his name and his work during your presentation. And Linto is there. Yes, Linto, I think
yes.
it is time all the 4 speakers are here, and you can wind up the today's session.
That's very nice. Thank you so much. We were really glad to listen to you all. It's a wonderful session. Actually, when Professor Van is here and Dr. Shekhar Lugos and Professor Thomas Uman is also here. So I was just thinking, we were earlier talking about something like managed retreat in our group, in teachers group, where Dr. Sajjan is also there. In Kerala's scenario, do we have a scope for that? Is there any chance that we somehow move away from the disaster-prone area and somehow settle in more of stable area? What is in a long-term aspect? Is it more economical and better way to think, or should we like rebuild in the same place? How do you think? What is your opinion on this?
Shaker will be the right person to answer.
Yeah, that's what I thought of asking here now.
Well, the idea is to populate people more densely towards safer areas. You should actually look at the Rebuild Kerala initiative documents that has come out. It's a very thick document, some 500 pages. The policy shift that we are looking at is to promote people to move out of vulnerable areas, which was legislatively favored in the past from the king's time, that we paid money to them to move uphill to vulnerable areas. Now we want to bring them back to clusters which are safe and leave away some places pristine. So in the Rebuild Kerala initiative document, that is the long-term vision that we have laid to transform the entire land use of Kerala, which would be conducive for the three different landscapes that we have, being the highlands, the midlands, and the low-lying parts of Kuttanad and the polder lands. So over time, that's what we are looking at. I'm not sure how successful that's going to be, but well, that's where the young minds have to be ignited towards thinking more scientifically in land use management. The core problem here is how we manage our land. And that's what we want to change. And that's what we are taking up as a mission under the Rebuild Kerala initiative. But that alone will not stop landslides from happening or disasters from happening. So be warned about that. That's still going to happen.
Thank you, Dr. Shekhar. That was a really nice thing to hear from you, that we do have a long-term plan. That is good to hear. Thank you so much. At this moment, I think we are already running out of time now. So I think with your permission, Sajin, should we stop now? Or is it time to conclude, or do you have to add?
we will conclude. Actually, I'm very much thankful to Shaker, Brian, Thomas, and Case, and finally to Lindo for this opportunity. I think the students who are participating in this one might have gained a lot from their presentation, and those are the people who has to bring Kerala or our community to the higher levels. Thank you all once again. Thank you, Brian, Shaker, Thomas, and Case. Once again, Lindo.
Thank you.
Okay.
I think Asha will conclude it now finally.
Okay. Before that, one announcement for all others who are participating in the first talk for tomorrow, where Tabas is delivering the talk. Actually, Zoom link is prohibited in Government of India offices, especially an organization like ISRO. So the thing is that I will be sharing a Google Meet link exclusively for the Tabas presentation, and the rest of the presentation will be in the Zoom. Actually, the third presentation by Vrindanath from UNEP, actually, she is having some inconvenience. So I am looking for an alternate person for that one, or if she will be able to join, she will be able to join for the third one. So I will be updating all those things in the Telegram group by early morning tomorrow. Thank you, Asha. Nice to meet you here.
Let me take a while to thank you, sir. I express my sincere gratitude to our session chair, Dr. Sajin Kumar KS. Because of a strict and efficient monitoring, we could complete it on time, and the session went really well. So I thank you, sir, and I thank all the eminent speakers and participants for their active participation. So tomorrow we have other interesting presentations waiting ahead. So see you all tomorrow. Thank you.
Okay.